The first humans on Mars will arrive beneath a sky no human being has ever stood under before. The daylight will be dimmer than daylight on Earth. Fine dust suspended in the atmosphere will tint the horizon. The ground beneath their boots will be untouched by human memory. Yet among all the unfamiliar objects around them, the one they may seek will not be on Mars at all. It will be Earth. From the Martian surface, our planet will not fill the sky. It will show no blue oceans, white clouds, green continents, or glow of cities. Without a telescope, it will appear as a point of light, bright under favorable conditions, but too small for human eyes to resolve as a world. A crew member looking toward it may know that everyone they have ever met is somewhere inside that point, while seeing none of the details that make it feel like home. That is the first contradiction of the journey. Earth will still be visible, but it will no longer look like Earth. The title of this story seems to promise something final. It suggests that the first people on Mars will watch Earth disappear and never see it again. Taken literally, that is not true. Earth does not permanently vanish from the Martian sky after a spacecraft lands. Robotic explorers have already photographed it from the surface. NASA's Curiosity rover recorded Earth and the Moon together in Martian twilight. Other rover observations have shown the planet as a remote, star-like light. When the sky is clear and the orbital geometry is favorable, a human observer should also be able to find it. But correcting the title does not make the mystery smaller. It makes the meaning of disappearance more difficult. A planet can remain visible while almost everything that once defined its presence has been removed. Its shape can disappear. Its colors can disappear. The faces, landscapes, and weather moving across it can disappear into a single unresolved point. Even the light reaching Mars is old, because it has spent minutes crossing interplanetary space. The Earth seen from Mars is never Earth at that exact moment. It is Earth as it was when those photons began their journey. Radio messages obey the same limit. A voice sent from Earth cannot arrive instantly, and an answer cannot return in real time. Depending on the changing distance between the planets, each half of an exchange can take several minutes or more than 20. The crew may be able to see the light of home while being unable to have an ordinary conversation with anyone living there. At certain times, even the point itself will be lost. Earth is an inner planet when viewed from Mars, so it remains in the general direction of the Sun rather than wandering across the entire Martian sky. As the orbital alignment changes, Earth can move into intense solar glare and become practically invisible for a time. Dust, daylight, terrain, and rare occultations can hide it as well. Yet these are temporary losses. The planets continue moving, the viewing angle changes, and Earth can return. So the real investigation cannot end with the question of whether human eyes can detect a distant light. Seeing is not a single condition. A camera can detect what an eye misses. A telescope can turn a point into a small disk. A radio can carry a message from a planet that cannot be seen. And a person can feel profoundly separated from a place that remains physically observable. For astronauts who have traveled before, Earth has always remained visually dominant or communicatively close. Crews in low Earth orbit circle beneath a vast moving globe. Apollo astronauts saw the whole planet suspended in blackness, but radio signals still crossed the distance in little more than a second. No human has lived where Earth is both visually insignificant and too far away for immediate contact. Mars changes both conditions at once. The first crew will not simply be farther from home than any previous explorers. They will operate across a delay that prevents Earth from participating in the immediate present. If equipment fails, If a medical decision must be made, or if conditions change quickly, expertise on Earth may still help, but it cannot erase the time already passing on Mars. Advice will arrive after the crew has begun confronting the problem themselves. This does not mean they will be abandoned. Missions can prepare procedures, autonomous systems, recorded guidance, and carefully designed communication routines. Families can exchange messages. Engineers can study data. Doctors can offer delayed support. The link between the planets may remain rich and continuous for long periods. But it will no longer feel like the connection humans know on Earth, where a question can interrupt an answer, and reassurance can arrive in the same emotional moment it is needed. There may also be intervals when orbital alignment interferes with direct communication. These periods will not be mysterious or unexpected. Mission planners can predict them. Still, knowing that silence is scheduled does not make it identical to ordinary delay. For a crew already living beside a small point of light, the temporary loss of messages may give astronomical geometry an intensely human consequence. This is why the disappearance in this story has to be tested in several different ways. First, there is the optical question. What will Earth actually look like, and when can human eyes see it? Second, there is the geometrical question. What movements of Earth, Mars, the Sun, the moons, and the atmosphere can temporarily remove it from view? Third, there is the temporal and operational question. What happens when every instruction, conversation, and request for help must cross millions of kilometers? Finally, there is the psychological question, the one for which no rover image or orbital calculation can yet provide a complete answer. What does a human mind experience when its home world becomes a delayed point in an alien sky? The evidence for these questions does not all have equal strength. We can calculate signal travel time. We can model planetary positions. We can examine photographs made from Mars. We can design mission timelines and communication procedures. But no human has yet experienced the full combination. The emotional consequences remain a risk to study, not a fate to declare. That uncertainty matters because it prevents a powerful idea from turning into a fabricated certainty. The first humans on Mars will not cross a magical boundary after which Earth ceases to exist. They may return to it. They may use instruments to view it. They may communicate with it throughout much of their mission. What changes is the relationship between visibility, presence, and home. Imagine the Martian observer looking again toward twilight. The point is still there. Astronomy says it has not been lost, but it contains a living world that cannot answer immediately, cannot intervene instantly, and cannot be seen in any recognizable detail. For the first time, a human being may look directly at Earth and experience it not as the surrounding world, not as a globe nearby, but as a remote celestial object. Earth has not disappeared. So what, exactly, has? To find what has disappeared, we have to begin with what Mars has actually shown us. Long before a human observer stands beneath the Martian sky, robotic cameras have already looked back in our direction. Their images are not imagined previews or artistic reconstructions. They are records made from the surface of another planet, using light that traveled from Earth across interplanetary space, before entering a camera built by human hands. In those images, Earth is present, but almost everything familiar about it is gone. One of the clearest examples came from NASA's Curiosity rover in January 2014. Curiosity was working inside Gale Crater when its mast camera was pointed toward the western horizon after sunset. The resulting view contained a bright object suspended in the fading Martian twilight. That object was Earth. A second, fainter point close beside it was the Moon. At the time, the two worlds were roughly 160 million kilometers from the rover. From Earth, that distance is normally discussed as a path for spacecraft or radio signals. From Mars, curiosity turned it into an image. Our planet and its natural satellite, together containing nearly every human life and every place in human history, occupied only a tiny part of the camera's frame. NASA noted that a person standing on Mars under comparable conditions could see Earth and the Moon as bright points without a telescope. That statement matters because it separates visibility from the capabilities of a scientific instrument. The camera did not reveal an object that was necessarily beyond all human perception. It preserved a view that an astronaut might one day seek with unaided eyes. But the published image also requires care. A rover camera is not a human eye. Its exposure can be selected for a dim sky. Images can be enlarged, combined, contrast adjusted, or presented through an inset that helps viewers locate an object occupying very few pixels. These operations do not invent Earth, but they can make the evidence easier to inspect than the original scene would have been during a casual glance. A processed picture answers the question, was light from Earth recorded here? It does not reproduce every detail of what a person would experience while standing beside the rover. That distinction is easy to lose when a space image reaches a screen on Earth. We see a cropped or enlarged frame, immediately read a label pointing to our planet, and then mentally restore the globe we already know. We supply blue oceans, cloud systems, and continents even when the photograph contains none of them. Recognition happens partly in the image and partly in the viewer. On Mars, an astronaut would not receive that assistance automatically. The sky would contain other bright objects. Dust could soften contrast. The horizon might be luminous after sunset. Earth's predicted position would be known, but finding it would still depend on timing, atmospheric clarity, and knowing exactly where to look. Once located, the point would carry enormous meaning, yet its appearance alone would not announce that it was a planet filled with people. Curiosity's observation was not the first time a machine on Mars had turned its camera homeward. A decade earlier, NASA's Spirit rover photographed Earth from the surface after sunset. The image was historically important because it demonstrated that our planet could be recorded as a celestial object from Martian ground, rather than from orbit or a passing spacecraft. Earth appeared as a small light above the horizon, embedded in a scene dominated by another world. The value of these observations does not come from spectacular detail. It comes from their restraint. They show exactly how little visual information can still represent an entire planet. The cameras did not return portraits of Earth. They returned evidence of its location. Later observations continued that record under different conditions. Curiosity photographed Earth and Venus in the Martian sky through noticeable dust. The scene showed why a simple statement such as, "Earth is visible from Mars," is incomplete. Visibility is not an on-off property belonging only to the planet. It depends on the brightness of the object, the state of the atmosphere, the background sky, the viewing angle, the sensitivity of the detector, and the observer's knowledge of where the object should be. A dusty sky can reduce contrast without erasing the source of light. Twilight can help by darkening the background while Earth remains above the horizon. A long exposure can gather photons that the eye receives continuously but interprets differently. Magnification can separate nearby points that would otherwise seem merged. Each change affects the view, even though Earth itself has not changed. This is why rover images have to be used as evidence rather than treated as exact simulations. They establish that photons from Earth reach the Martian surface and that cameras have repeatedly recorded them. They also support the expectation that a trained observer could detect Earth under suitable conditions. They do not establish that Earth would always be obvious, always separate from the Moon, or always look as bright as it does in a carefully prepared publication. The difference becomes especially important in the image of Earth and the Moon together. From the surface of our planet, the Moon is a large, detailed object. Its phases shape calendars, tides, stories, and the appearance of the night. Seen from Mars, the same Moon is compressed into a much fainter light near Earth. The pair no longer presents itself as a planet with a large companion. It resembles 2 points whose identities must be inferred from their positions. That image reverses the ordinary hierarchy of the sky. On Earth, the Moon can dominate the night, while our planet remains the ground beneath the observer. From Mars, Earth and Moon are both moved into the heavens. The world that once surrounded the viewer becomes an object, and the object that once crossed the viewer's sky becomes a neighboring speck. Even then, the camera records more than a symbol. The light in those pixels has a physical origin. Some of it was sunlight reflected by Earth's clouds, atmosphere, oceans, ice, and land. Some of the fainter light near it was reflected by the Moon. The image contains real information carried across the gap, yet the information is compressed so severely that the structures producing it cannot be distinguished by the unaided eye. That compression creates a strange boundary between knowledge and perception. An astronaut could know that weather systems are moving across Earth, that night is falling over particular countries, and that billions of people are continuing their lives there. None of those facts would be visible in the point itself. The observer would know far more about the object than the object appears to reveal. This is not unique to Earth. Stars have always confronted human vision with the same problem. A point of light can represent something physically enormous. But Earth would be different because its hidden detail would not be abstract. The missing information would include familiar places, current events, and people whose messages might already be traveling toward Mars. It would be a point whose significance came almost entirely from knowledge acquired before the journey. The rover images therefore offer 2 kinds of proof. The first is straightforward. Earth does not permanently disappear merely because an observer reaches Mars. It has been photographed from Martian ground more than once. The second is more unsettling. Being visible is not the same as being visually present as a world. An image can also change with presentation. A wide rover panorama may make Earth nearly impossible to notice until an inset identifies it. A crop can place it at the center. Enlargement can transform 1 or 2 bright locations in the original data into an obvious marker on a large screen. Color balance can make the Martian twilight feel more natural to human viewers or emphasize differences between channels. None of these choices should be confused with fabrication, but none should be ignored when asking what a future astronaut would see. The safest conclusion is narrower and stronger than the dramatic version. Under favorable geometry and reasonably clear conditions, Earth can send enough visible light to be detected from the Martian surface. Cameras have demonstrated that fact. A person may also see it as a bright point, particularly when its location is known and the surrounding sky is dark enough. But the direct observations do not promise an uninterrupted view, a constant brightness, or a recognizable blue disk. Nor do they tell us how the first human observer will respond. A rover has no childhood memories attached to the point in its image. It does not understand that the small light contains the place where it was designed, assembled, tested, and launched. It records photons without homesickness, relief, or fear. Human eyes would bring a history that the camera cannot measure. Perseverance has extended this observational record. Its images confirm the same basic fact, while also showing that Earth can participate in events within the Martian sky rather than remaining a fixed marker. In one documented sequence, the tiny source was briefly covered by Phobos, the fast-moving inner moon of Mars. The mechanics of that disappearance belong later in the investigation. Here, its value is simpler. The camera could identify Earth before the event, follow its position, and record its return. A point that looks almost insignificant can still be measured with enough precision to become part of a predictable celestial alignment. Taken together, the rover observations span different instruments, locations, dates, atmospheric conditions, and purposes. No single frame should carry the entire argument. Their strength comes from agreement. Earth repeatedly appears where planetary motion says it should appear. The exact presentation varies, yet the underlying signal remains. That repeated detection is more reliable than an artist's impression of a large blue globe hanging over the horizon. The real view is less visually generous, but scientifically more compelling. Our planet reaches Mars not as an illustration of home, but as measurable light. For now, however, the emotional question has to wait. The evidence baseline must remain physical. Spirit, curiosity, and later surface observations have shown that Earth can occupy the Martian sky as a detectable source of light. They have shown that the moon may appear nearby. They have shown that atmosphere, twilight, camera settings, and image presentation affect how clearly the pair can be identified. And they have shown that a world does not need to vanish completely for nearly all of its visible character to be lost. The photographs settle the first dispute. Earth will be there, but they leave behind a scale paradox. How can a planet large enough to hold oceans, weather, continents, and billions of lives arrive at the human eye looking no wider than a star? The answer begins with a distinction that human vision often hides from us. Brightness and size are not the same thing. An object can send enough light into the eye to be noticed while remaining far too small for the eye to distinguish its shape. Every clear night on Earth demonstrates this. The brightest stars can be unmistakable, yet none looks like a sphere to unaided vision. Each remains a point. Its light may be strong, but the angle it occupies in the sky is too narrow for the eye to resolve its surface. Earth presents the same paradox from Mars. Under favorable conditions, it may be one of the brighter point-like objects in the Martian twilight. Calculations summarized in the research record place its brightness near an apparent magnitude of -2.5 at a favorable part of its cycle. That figure is not a permanent value. Earth's brightness changes with distance, phase, viewing geometry, atmospheric conditions, and the brightness of the surrounding sky. But the estimate makes one point clear. Our planet does not need to be faint in order to look insignificant. Astronomers describe apparent brightness using the magnitude scale. The system runs in a direction that initially feels backward. Smaller and more negative numbers describe brighter objects. The number does not tell us how large an object looks. It records how much light reaches the observer through a particular viewing band. A distant source can therefore be bright while occupying almost no visible width. That is why brightness can help an astronaut find Earth without helping the astronaut recognize it. Recognition depends on angular size. The angle an object appears to span from one side to the other. Physical diameter is only part of that calculation. Distance controls how much of the observer's field of view the diameter occupies. Bring an object closer and its angular size grows. Move the same object away and its angular size shrinks, even though the object itself has not changed. Hold a coin close to one eye and it can cover the moon. Move the coin across a room and it becomes a tiny circle. The coin's diameter is unchanged. Only the viewing angle has altered. Earth seen from Mars follows the same principle across a vastly greater distance. The research calculations for the full Earth-Mars distance cycle place Earth's apparent diameter at roughly 7 to 48 arcseconds, depending on where the planets are in their orbits. An arcsecond is 1/3600th of a degree. It is a unit designed for angles so small that ordinary language becomes clumsy. Even at the larger end of that range, Earth would remain a tiny target. At the smaller end, it would be compressed to only a few arcseconds across. For comparison, the full moon seen from Earth spans roughly half a degree, or about 1800 arcseconds. This comparison is useful only for scale. Earth from Mars does not behave exactly like our moon in brightness, phase, or motion. But in apparent width, the difference is enormous. At its most favorable in the sighted range, Earth would still look dozens of times narrower than the full moon appears from Earth. At the far end, the difference would grow to hundreds of times. The eye cannot simply enlarge a small object because the observer knows it is important. Light entering through the pupil is focused onto the retina, where the available detail is limited by optics, receptor spacing, contrast, atmospheric distortion, and the observer's vision. Under excellent conditions, a healthy human eye can separate features roughly around an arc-minute apart, although real performance varies. An arc-minute contains 60 arcseconds. Most of Earth's calculated apparent size range from Mars falls below that broad naked-eye resolution scale. Resolution is also different from merely noticing that two sources are present. A bright point can stimulate several retinal receptors because optics spread light rather than producing a mathematically perfect dot. That apparent patch is not a resolved image of the object's physical surface. It is the response of the eye to light arriving from an angle narrower than the eye can analyze. The point may seem sharp, soft, or slightly colored without revealing Earth's true outline. The nearby moon creates another version of this limit. A camera with adequate sampling may record two separate sources and allow an enlarged publication to show both. Human vision may see a companion only when their separation, brightness contrast, atmospheric clarity, and observing conditions cooperate. If the fainter moon blends into Earth's glare, the observer would not see a miniature version of the familiar Earth-Moon system. The pair could collapse into one dominant point or appear as two lights whose physical identities are impossible to infer from appearance alone. This is why the threshold should not be described as a hard wall applying identically to every observer. Eyes differ. Contrast changes. Dust scatters light. Twilight can either help by reducing glare from the surface or hinder by brightening the background near the horizon. Astronauts could improve their chances by shielding stray light, allowing their eyes to adapt, and using precise positional guidance. These measures help detection. They do not enlarge the angle subtended by Earth. This does not mean Earth's light disappears. It means the light is blended into a point-like image before the visual system can extract a clear edge. The observer may detect brightness and position without seeing a disk. Color is also difficult to judge in a tiny source, especially in twilight or through suspended dust. The blue planet can therefore reach the eye without arriving as a visibly blue world. The phrase "see Earth" now divides into two meanings. One meaning is detection. Enough light is present for the observer to notice a source at the predicted location. The other is resolution. The observer can distinguish the source as an extended object with shape or surface detail. From Mars, unaided human vision may achieve the first while failing at the second. This is the boundary that rover images can blur when they are enlarged for publication. A camera places light onto an array of detector elements. If Earth covers only a small number of those elements, software can enlarge the result until the mark is obvious on a screen. Enlargement makes the recorded pattern easier to inspect, but it does not recover unlimited detail. A larger display of a few measured pixels is still based on a few measured pixels. Longer exposures can also make a source easier to detect by collecting light over time. Different filters may record different portions of the spectrum. Multiple frames can reduce noise or help distinguish a persistent celestial object from random detector variation. These techniques are scientifically valuable because they reveal signals that would otherwise be difficult to inspect. Yet none turns the original naked eye view into a nearby globe. A telescope changes the problem more fundamentally. Its larger aperture gathers more light, and its optics create a magnified image with greater resolving power than the unaided eye. Under suitable conditions, an instrument on Mars could separate Earth from the Moon more reliably and might resolve Earth as a tiny disk when its apparent size and the telescope's performance permit. More capable imaging systems could record phase and perhaps broad variations in brightness. But even then, the familiar satellite portrait of Earth would not simply hang in the sky. Detail would have to be recovered through equipment, careful pointing, exposure, and processing. The distinction matters emotionally because instruments and eyes answer different human needs. A telescope could confirm that Earth is still there. It could provide data and perhaps a small resolved image. But the naked eye sky would continue presenting home as a light among other lights. Technology could restore information without restoring the immediate visual presence that astronauts experience near Earth. Brightness itself would also refuse to remain constant. Earth and Mars do not sit at fixed points separated by a single permanent distance. Both orbit the Sun, and their separation changes dramatically. The portion of Earth's sunlit side facing Mars changes as well. A larger apparent disk is not automatically the brightest possible view, because distance, illumination, phase, atmospheric extinction, and solar glare interact. Consider a familiar example from Earth. Venus is sometimes the brightest object in the evening or morning sky after the Sun and Moon, yet it still looks like a point without optical aid. Through a telescope, Venus reveals phases. Its greatest apparent size does not always coincide with the configuration that makes it easiest or brightest to observe. The analogy is limited, but it helps reverse the Martian viewpoint. From Mars, Earth is an inner planet. Its brightness and phase are tied to changing orbital angles rather than a simple rule that closer always means clearer. The full geometry belongs to the next step of the investigation. For now, the important result is that no single picture or number can represent the Martian view for an entire mission. The sighted diameter range spans nearly an order of magnitude. Apparent brightness changes. The Moon's separation from Earth changes. Dust and twilight alter contrast. An astronaut may see an obvious point during one observing window and struggle to locate it during another. Even the phrase "naked eye visible" must be understood as conditional. It does not mean every person could step outside at any hour and immediately identify Earth. Visibility depends on clear enough air, a sufficiently dark background, the object remaining above the local horizon, and the observer knowing where to look. A trained crew, equipped with predicted sky positions, would have an advantage. A casual observer under a bright or dusty sky might overlook the same source. This makes the first human observation more subtle than the dramatic image of a blue marble over a red desert. The crew would not discover Earth through visible continents or a recognizable crescent. They would identify it by combining a point of light with knowledge, navigation data, time, direction, and orbital predictions. Science would tell them which point was home. Once identified, the point could become psychologically immense while remaining optically minute. Every ocean would be present but unresolved. Every cloud would reflect light but vanish into the combined signal. Day and night would divide the planet, yet the naked eye might not distinguish the boundary. The physical Earth would remain richly detailed. Only the arriving image would be stripped down. That loss of detail is not an illusion created by poor cameras. It is the natural consequence of perspective. Across millions of kilometers, a diameter of more than 12,000 kilometers can occupy less sky than the eye needs to perceive an edge. Distance does not remove the planet. It compresses the information the observer can recover from it. This also explains why photographs from Mars can be scientifically honest and emotionally misleading at the same time. The data truly contains Earth. The label correctly identifies it. The enlarged frame accurately guides attention. But viewers on Earth encounter the image with a screen, a caption, and a lifetime of close views of their planet. A crew member encountering the original sky would receive only the light, then supply the meaning internally. The scale paradox is therefore resolved. Earth can be bright because it reflects sunlight. It can be visible because enough of that reflected light reaches Mars. And it can remain unrecognizable because the angle it occupies is too small for unaided eyes to separate into a disk or surface features. Brightness reveals presence. Angular size limits identity. But that answer carries its own limitation. The numbers are not fixed because the distance and illumination are not fixed. Earth can grow, shrink, brighten, dim, separate from the sun, or move toward its glare as the planets continue around their orbits. The point is not placed permanently in one part of the Martian sky. To understand when the first crew could find it, we have to leave the static image behind and set the planets in motion. Setting the planets in motion begins by changing the observer's address. On Earth, we divide the planets into familiar patterns. Venus and Mercury remain near the Sun in our sky, appearing before sunrise or after sunset, rather than crossing the midnight sky like Mars or Jupiter can. That behavior is not an intrinsic label carried by the planets. It comes from geometry. Venus and Mercury orbit closer to the Sun than Earth does, so an observer on Earth always sees them within a limited angle of the Sun. Move the observer to Mars, and Earth joins that inner group. Earth still follows the same orbit it has always followed. Nothing physical happens to our planet when the viewpoint changes. But from Mars, Earth now travels around the Sun on an orbit lying inside the Martian one. To a person standing on the Martian surface, our homeworld would behave in broad terms like an interior planet. It could appear in the eastern sky before the sun or linger in the west after sunset. It would never roam arbitrarily far from the sun's direction. This reversal is more than a useful astronomy lesson. It determines whether the first crew could step outside at midnight and look straight up for home. Usually, they could not. Earth's place in the Martian sky would be governed by its apparent separation from the Sun, an angle astronomers call elongation. Imagine drawing two lines from an observer on Mars. One line points toward the Sun, the other points toward Earth. The angle between those lines is Earth's elongation. If the angle is wide enough, Earth can remain above the horizon while the Sun is below it, placing the planet in a darker portion of the sky. If the angle narrows, Earth moves deeper into the bright regions surrounding sunrise or sunset. When it becomes very small, solar glare can overwhelm the point even though Earth continues reflecting light. From Mars, Earth's maximum separation from the Sun is about 47 degrees. The exact viewing circumstances change continuously, but the limit establishes the basic shape of every observing window. Earth may pull far enough from the Sun to become a conspicuous morning or evening object. It cannot appear on the opposite side of the sky at Martian midnight, because its orbit never carries it outside the Sun as seen from Mars. The easiest way to imagine this is to watch Venus from Earth. For part of its cycle, Venus shines after sunset. Over time, its position changes until it moves toward the Sun and disappears into glare. Later, it emerges on the other side as a morning object before sunrise. Earth follows an analogous pattern for a Martian observer. The analogy has limits. Earth is not Venus. The planets differ in size, reflectivity, atmosphere, moons, orbital properties, and the distances involved. Mars also has a different day length, atmosphere, horizon brightness, and dust environment. The comparison explains the geometry of an inner planet, not an identical visual experience. Within that geometry, the terms morning star and evening star describe timing rather than the nature of the object. Earth is never a star. It shines mainly by reflecting sunlight. But when its unresolved image appears before sunrise, it can look star-like. When it remains visible after sunset, it becomes Mars's evening light. The name tells an observer when to search. Suppose Earth lies east of the Sun in the Martian sky. As Mars rotates, the Sun sets first, while Earth remains above the western horizon for a time. The darkening background improves the contrast, creating an evening viewing window. If Earth lies west of the Sun, it can rise before the Sun and occupy the eastern sky during Martian dawn. The orbital arrangement decides whether home is sought at the beginning or end of the night. The window does not stay fixed from one sol to the next. Earth moves around the Sun faster than Mars because its orbit is smaller and its year is shorter. Mars also moves, so the apparent position results from both motions combined. The angle between Earth and the Sun gradually widens, reaches a maximum, and narrows again. Across this cycle, the planet shifts against the background sky, while its phase, distance, and brightness change together. The complete pattern repeats according to the Earth-Mars synodic cycle, roughly 26 months. This is the interval required for the two planets to return to approximately the same relative arrangement around the Sun. The same broad rhythm helps determine launch opportunities between the planets. For a crew on Mars, it would also govern recurring changes in Earth's position and in the communication geometry explored later. One way to picture the cycle is to imagine looking down on the solar system from above its orbital plane. Earth travels on the smaller track and completes each circuit sooner. Mars advances along a wider track more slowly. At one stage, Earth lies roughly between Mars and the Sun. From Mars, the planet then appears close to the Sun's direction and shows mostly the hemisphere turned away from the sunlight. As Earth races ahead, the angle at Mars opens. the planet pulls away from the sun in the sky and becomes available during morning or evening twilight. Later, the angle closes on the opposite side, returning Earth toward glare. Continue the motion until the sun lies approximately between the two planets. Earth is then near the far side of the solar system from Mars. Its sunlit hemisphere faces toward the Martian observer, but its apparent position again lies near the sun. Greater illumination cannot compensate for a background dominated by solar light. The cycle therefore contains two different routes toward a small elongation. One when Earth is on the near side of the sun from Mars, and another when it lies beyond the sun. These arrangements are often described with terms such as inferior and superior conjunction. The labels identify geometry, not the quality of the view. For this investigation, their practical importance is simple. At either narrow alignment, Earth approaches the part of the sky where observing becomes most difficult. At wider angles, it returns to the morning or evening sky. The point does not wander randomly. Its disappearance and return emerge from a clockwork pattern created by two planets moving at different rates. Yet calling it a repeating cycle should not suggest that every view is identical. Mars follows a noticeably elliptical orbit, and Earth's orbit is not a perfect circle either. A crew's landing site, local season, atmospheric dust, and horizon all affect observing conditions. The geometry is predictable, but the human view occurs from a particular place at a particular time. Earth's phase adds another layer. Because Earth reflects sunlight, an observer on Mars sees a changing fraction of its illuminated hemisphere. When Earth appears far from the sun in the sky, the viewing angle can expose a larger portion of its day side than in other arrangements. Near configurations where Earth lies between Mars and the sun, a Martian telescope could see more of Earth's night-facing side, producing a thinner illuminated phase even as the planets may be relatively close. This creates a counterintuitive trade-off. Bringing Earth closer does not guarantee that it will look brightest or easiest to observe. A closer Earth may present a less fully illuminated face. A more distant Earth may show a greater illuminated fraction but occupy a smaller angle. Solar glare can dominate both effects when the apparent separation from the sun becomes narrow. Venus again offers a limited guide. Through a telescope from Earth, Venus can become physically larger in apparent diameter as it approaches us, while its visible phase becomes a thinner crescent. At other times, it appears smaller, but more fully illuminated. Its greatest brilliance emerges from a balance among distance, apparent size, and illuminated fraction. Earth from Mars is governed by the same categories, although not by identical values. To unaided human eyes, the changing phase of Earth would usually be hidden inside the unresolved point. The total light could change, but the observer would not necessarily see a tiny crescent become a gibbous disk. A telescope could reveal more. This produces another separation between physical reality and direct experience. Earth can pass through a sequence of phases without the crew seeing the shape of those phases unaided. The Moon complicates the pattern on a smaller scale. It travels around Earth, changing its apparent separation and illumination as seen from Mars. Sometimes a camera may distinguish the 2 points. At other times, their angular separation or brightness difference could make the Moon difficult to identify without suitable equipment. The Earth-Moon pair therefore has its own motion nested inside the larger movement around the Sun. But the Moon does not control the main observing window. That window belongs to the changing Sun-Earth-Mars angle. An astronaut planning to view Earth would use predicted positions rather than scan the whole sky. Mission software could provide direction and time. The crew might know that Earth would become visible low in the west after sunset, climb or descend along a calculated path, and then set. On another part of the cycle, the search would shift to dawn. Mars itself adds the daily motion. As the planet rotates once every sol, the sky appears to rise in the east and set in the west. Earth participates in that apparent daily sweep, while its slower orbital position changes from one sol to the next. The result resembles a celestial appointment that moves gradually across the calendar. Local geography would shape that appointment. A crater wall, ridge, habitat structure, or nearby terrain could block a low-altitude view. Dust close to the horizon could scatter sunlight and reduce contrast. A viewing site with a clear horizon might reveal Earth earlier or retain it later than a sheltered base. The planet's astronomical position can be known precisely while the practical view remains local. This explains why no fixed instruction, such as "look west at sunset," would work for an entire mission. The direction changes with the orbital cycle. Morning becomes evening. The angle grows and contracts. The planet brightens and dims. Its apparent size changes as the distance between the worlds changes. Even when the source is theoretically above the horizon, the background sky may decide whether the eye can separate it. The motion also changes the emotional character of the view. At a favorable elongation, Earth could appear detached from the Sun, placed against darker twilight and easier to identify. Over subsequent sols, the point could migrate closer to the bright horizon. The crew would know that its disappearance was approaching, not because Earth was moving away into an unknown region, but because predictable geometry was carrying it toward the Sun's glare. That predictability is important. Nothing about the event requires Earth to be destroyed, extinguished, or permanently abandoned. The light is not switched off. The line of sight is being compressed toward the brightest object in the sky. Observation fails because the contrast becomes unfavorable, not because the planet stops reflecting sunlight. It also means that disappearance and distance are not identical. Earth can be farther away, yet well separated from the Sun in the Martian sky, creating a usable observing window. It can be closer while appearing near the Sun, where glare makes it difficult or dangerous to observe directly. The relevant question is not only how many kilometers lie between the worlds, it is where Earth appears relative to the Sun and how much of its illuminated side faces Mars. With those pieces combined, the changing view becomes understandable. Earth is a point because distance reduces its angular size. It becomes a morning or evening object because its orbit lies inside Mars's orbit. Its brightness varies because distance and phase vary. Its visibility rises and falls because elongation changes the contrast between the point and the surrounding sky. For much of the cycle, the first crew could in principle recover Earth by waiting for the correct time, looking in the predicted direction, and using the appropriate instrument or unaided vision when conditions permit. But the same orbit that creates those opportunities also carries the planet toward conditions where finding it becomes impossible. The viewing angle narrows. Twilight brightens around the point. Earth approaches the Sun's apparent position until reflected light from an entire planet is overwhelmed by glare scattered through the Martian sky and the observing system. Geometry has not removed Earth from the universe. It has removed the contrast required to see it. And solar glare is only one way that can happen. Solar glare is the most predictable way for Earth to disappear, but it is not the only one. A planet can be hidden by geometry, atmosphere, landscape, daylight, or another moving object. Each mechanism removes the view for a different reason, on a different scale, and for a different length of time. The distinction matters because the word disappear makes all absence sound alike. It can suggest that Earth has crossed a permanent boundary or become too distant for its light to reach Mars. Neither is required. In most cases, Earth continues sending reflected sunlight toward the Martian surface. What changes is the observer's ability to separate that light from everything around it. The clearest example occurs as Earth moves toward the Sun's apparent position. The elongation described earlier becomes smaller. An astronaut searching near dawn or dusk must look into a region of the sky increasingly dominated by sunlight scattered through the atmosphere and the observing system. Earth's photons still arrive, but the contrast that made the point detectable begins to collapse. This is similar to trying to see a small lamp placed beside a searchlight. The lamp has not switched off. Move the searchlight away, and the lamp becomes obvious again. Place both sources close together in the field of view, and the brighter source overwhelms the weaker one, scattering light across the scene and inside the eye or camera. The analogy has an important boundary. The sun is not merely a bright object positioned near Earth in the sky. It is the source illuminating Earth, and its apparent proximity results from the orbital alignment of three moving bodies. The geometry changes continuously. Solar glare is therefore not a permanent curtain. It is a predictable interval within a cycle. Near conjunction, Earth can become practically unobservable from the Martian surface for an extended period. The precise visibility window cannot be reduced to one universal number. It depends on how close Earth appears to the Sun, the instrument being used, the Martian atmosphere, local horizon conditions, safety limits on pointing equipment near the Sun, and the threshold chosen for detection. A camera designed for one purpose may stop observing before another instrument would. The instrument itself can create a boundary before nature does. Optical systems scatter a small fraction of incoming sunlight inside lenses, mirrors, housings, and detectors. That stray light raises the background against which Earth must be measured. Sensors may saturate. Protective rules may prohibit pointing close to the sun, and a telescope designed for surface geology may tolerate less solar exposure than a dedicated solar instrument. Consequently, not observable can mean that the available equipment cannot make the measurement safely, not that no conceivable instrument could detect any photons from Earth. Human observers face a stricter safety limit. Looking near the sun can damage the eye, and the fact that Earth lies somewhere in the same direction does not justify attempting it. The first crew would use predicted geometry, approved filters, cameras, or wait for safer separation. The absence they experience would therefore be partly biological and operational. The planet exists in the field, but responsible observation has to stop. For the unaided eye, the practical limit can arrive well before exact alignment. As the sky brightens, the pupil contracts and contrast falls. Dust suspended in the Martian atmosphere scatters sunlight, especially near the horizon. A point that was easy to identify against dark twilight can fade into a luminous background, even while a sensitive instrument might still recover it. This creates several different meanings of gone. Earth may be below the sensitivity of unaided vision, but present in a camera image. It may be detectable by an instrument that is not safe or useful when pointed close to the sun. It may remain mathematically above the horizon while being lost in dust and scattered light. Or it may lie so close to the sun's apparent position that no practical surface observation can separate the two. None of these states is permanent. As Earth and Mars continue along their orbits, the apparent angle begins to widen again. The point eventually emerges on the other side of the sun's glare, changing from an evening object to a morning object, or the reverse. Its return is generated by the same geometry that hit it. But orbital alignment is only the largest scale cause. Mars itself can block the view every sol. Like every celestial object, Earth rises and sets because Mars rotates. When the planet lies below the local horizon, the solid body of Mars stands between the observer and the incoming light. This is ordinary occultation by the planet under the observer's feet, not an interplanetary disappearance. A person at another longitude may have a different viewing window at the same moment. Local terrain can shorten that window. A crater rim, ridge, cliff, habitat, vehicle, or dust-covered slope may obstruct a low point before the astronomical horizon would. A base placed for engineering safety, rather than sky visibility, could have restricted lines of sight. The predicted position may be exact, yet the observer's landscape still decides whether the point is accessible. Daylight produces another practical limit. Earth does not have to be beside the sun to become difficult to see in a bright Martian sky. If it is above the horizon while the sun is also high, the background can wash out a source that would be conspicuous after sunset. A sufficiently capable instrument may locate it, but the naked eye experience changes. Earth is above the horizon, and a person can see Earth are not equivalent statements. Then there is dust. Mars has a thin atmosphere, but it carries fine particles capable of transforming the sky. Local and regional dust activity can increase opacity, reduce contrast, and alter the color and brightness around the horizon. At times, dust can spread across much of the planet. The effect on a particular Earth observation depends on optical depth, viewing direction, solar angle, and instrument sensitivity. It would be irresponsible to assign one fixed duration to every obscuration. Dust does more than place a uniform veil over the heavens. Particles redirect sunlight through the sky, changing background brightness differently with direction and solar angle. Near the sun, additional scattering can be especially damaging to contrast. Near a darker region, a bright planet may survive longer. The same amount of dust can therefore affect two observations differently. What matters is not merely how much light Earth supplies, but how that light compares with everything the atmosphere sends into the same detector or eye. A storm also develops over time. The point may fade gradually rather than blink out. Cameras can track the decline, adjust exposure, or change filters, while an unaided observer loses confidence earlier. Later, as opacity falls, an instrument may recover Earth before a person notices it. Disappearance and return can have different thresholds depending on who or what is looking. NASA's Curiosity rover has photographed Earth and Venus through dusty Martian conditions, demonstrating both the persistence of the signal and the challenge of the background. Dust does not automatically erase every bright object. It gradually changes the contrast between the source and the scattered light. During mild conditions, Earth may remain recoverable. Under heavier opacity, the point may become difficult or impossible to identify from the surface until the atmosphere clears. This form of disappearance differs from conjunction in a crucial way. Solar geometry can be calculated far in advance with extraordinary precision. Dust can be monitored and modeled, but its local effects introduce meteorological uncertainty. A crew may know exactly where Earth should be and still fail to see it because the atmosphere between the observer and space has changed. The atmosphere therefore becomes part of the image. The light from Earth does not travel directly into an astronaut's eye after crossing empty interplanetary space. Its final path passes through Martian air, however thin, and through whatever dust occupies that line of sight. The last few kilometers can determine whether light that survived millions of kilometers remains visible. There is also a more dramatic, much shorter way for Earth to vanish. Another object can cross directly in front of it. Mars has two small moons, Phobos and Deimos. Phobos is the closer and faster moving of the pair, orbiting so near the planet that it crosses the Martian sky rapidly. Because Earth is point-like from the surface, a precise alignment can allow the apparent shape of Phobos to cover it. For the duration of that alignment, the incoming light is physically blocked. NASA's Perseverance rover documented such an event from the Martian surface. In the recorded sequence, Earth approached the apparent path of Phobos and was occulted by the Moon. The point disappeared behind Phobos and later returned. The observation was rare and visually striking, but its scientific meaning must remain exact. Phobos did not remove Earth from the sky permanently. It interrupted one line of sight for a short interval from one location on Mars. Unlike fading in dust or glare, an occultation has comparatively sharp geometry. Before contact, Earth remains detectable beside the Moon's approaching silhouette. During overlap, the solid body of Phobos blocks the direct path. Afterward, Earth emerges. The sequence provides a clean distinction between a source becoming too difficult to separate from its background and a source being physically covered. Both produce absence in an image, but their light paths fail in different ways. That difference is scientifically useful. Timing when Earth disappears and reappears can test predicted positions and the apparent outline of the intervening Moon. The event is not only a symbolic picture of home being erased. It is an observation produced by known orbital motion, precise viewpoint, and measurable boundaries. Its emotional power comes from the accuracy of the alignment, not from exaggerating its duration. An occultation is not the same as an eclipse of Earth itself. The event belongs to the observer's perspective. Shift the observing location far enough and the alignment changes. Wait while Phobos moves along its rapid orbit and the line of sight opens again. The disappearance is complete for that view, but sharply limited in place and time. This makes the event a useful demonstration of scale. A moon only a few tens of kilometers across can hide a planet more than 12,000 kilometers across because apparent size depends on distance. Phobos is tiny compared with Earth, but it is extraordinarily close to the Martian observer. Its angular width can therefore exceed the angular width of the remote planet. A nearby small object covers a distant large one. The effect is familiar on Earth, where the Moon can cover the much larger Sun during a solar eclipse. The physical sizes are radically different, but their apparent sizes can align. From Mars, an Earth occultation by Phobos follows the same basic rule of perspective without reproducing the same appearance or duration. For a future crew, such an event would be predictable with accurate ephemerides and local coordinates. It could become a planned observation rather than a sudden cosmic loss. Cameras might be pointed in advance. Timings could test orbital predictions. The emotional interpretation would belong to the observers. The physical event would remain a measurable alignment. There may be other brief interruptions as equipment, habitat windows, vehicles, or the observer's own movement changes the line of sight. These events reinforce the central rule. Visibility always belongs to a particular observer, location, time, atmosphere, and instrument. Saying that Earth is visible from Mars describes a possibility, not an uninterrupted service. Saying it has disappeared describes an observation, not necessarily a change in Earth. Before attaching meaning to any absence, the crew must first identify which link in the chain of visibility has failed. Taken together, these mechanisms form a hierarchy of disappearance. The rotation of Mars places Earth below the horizon as part of every relevant daily cycle. Local terrain can shorten access to a low view. Daylight and dust can reduce contrast. Orbital motion can carry Earth into solar glare for a much broader interval. Rarely, a moon can cover the point directly. They should not be blended into one dramatic claim. Horizon loss is local and routine. Dust is atmospheric and variable. Conjunction is astronomical and predictable. A Phobos occultation is brief, geometric, and location-dependent. Each causes genuine invisibility under its own conditions, but none demonstrates that Earth has gone forever. Even the strongest optical disappearance contains the mechanism of return. Mars rotates, revealing the sky again. Dust settles or moves. Phobos crosses the line of sight and departs. Earth and Mars advance around the Sun until the angular separation widens. The point can be reacquired by the eye, camera, or telescope when conditions once again permit. This resolves the literal promise in the title. The first humans on Mars may indeed watch Earth disappear. They may lose it behind solar glare, beneath a horizon, inside a dust-brightened sky, or for a moment behind Phobos. But astronomy offers no reason to claim that they can never see it again. The disappearances are events, not an irreversible state. That answer might seem reassuring. Home returns. A predicted point emerges from twilight, and the crew can locate it again. Yet reacquiring the image restores only visibility. It does not restore the conditions under which humans have always known Earth. Every photon in that point has spent time traveling. Every image received from Earth began its journey earlier. Every radio message crosses the same changing gulf. The crew may be looking directly at home while seeing a version of it that no longer exists in exactly that moment. The optical mystery is over. Earth can disappear, and Earth can return. The deeper mystery begins when distance stops being measured only in kilometers and starts being measured in time. Light makes every return possible. It is also the reason no return is immediate. When Earth reappears in the Martian sky, the photons entering an astronaut's eye have already completed a journey across interplanetary space. The point looks present, but the image is historical. Earth is being seen not as it is at the observer's moment, but as it was when the light left. This delay is not caused by weak equipment, limited bandwidth, slow computers, or an unfinished communications network. It comes from the finite speed at which information can travel. In a vacuum, light moves at just under 300,000 kilometers per second. Radio waves are part of the same electromagnetic family, so they obey the same limit. A more powerful transmitter can make a signal easier to receive. It cannot make the signal arrive before light could cross the distance. On Earth, that limit normally hides beneath ordinary experience. Light can travel around the equator several times in a second. A video call may feel delayed because of routing, processing, congestion, or software, but the direct light travel time across terrestrial distances is tiny. Human conversation evolved in a world where the physical propagation delay between nearby people is effectively invisible. Mars removes that convenience. The delay is therefore not a nuisance added to the mission. It is part of the physical environment the mission must inhabit every day. Even when Earth and Mars are comparatively close, They remain separated by tens of millions of kilometers. At greater separation, the path can extend across hundreds of millions. A signal crossing that gap accumulates minutes of unavoidable travel time. NASA communication studies for representative Mars conditions describe one-way delays ranging from roughly 3 or 4 minutes near favorable separation to more than 20 minutes when the planets are far apart. Exact values depend on their positions and on the mission trajectory. The phrase one-way delay is essential. It measures only the path from sender to receiver. If a person on Mars transmits a question when the one-way light time is 10 minutes, Earth cannot receive that question before roughly 10 minutes have passed. If someone on Earth responds immediately, the answer requires another 10 minutes to return. The earliest possible exchange has already consumed about 20 minutes before allowing any time for receiving, reviewing, deciding, recording, or transmitting. 3 representative cases make the changing rhythm easier to grasp. With a 4-minute one-way delay, a message sent from Mars reaches Earth 4 minutes later, and an immediate response cannot return before about 8 minutes have passed. With 12 minutes each way, the physical minimum becomes roughly 24 minutes. With 22 minutes each way, it becomes about 44. These are examples drawn from the broader range, not fixed stages that every mission follows on an exact timetable. The arithmetic also assumes an immediate reply, which almost never exists outside a thought experiment. Receiving equipment must identify and reconstruct the signal. Software may check errors. People may need to interpret the content. A response must be created and scheduled for transmission. The round-trip light time therefore describes the fastest boundary permitted by physics, while an operational answer usually takes longer. This boundary cannot be defeated by predicting what the other side will say. Software might anticipate routine needs, preload procedures, or generate local assistance. Mission planners can send likely answers before a question is asked. Those strategies reduce dependence on a future reply, but they do not carry new information from Earth faster than light. Prediction substitutes preparation for communication. It does not alter causality. At a one-way delay above 20 minutes, the physical round trip alone can approach or exceed 40 minutes. That is not always the delay, and it should never be presented as one fixed property of Mars. It is the high end of a changing range. At closer configurations, the round trip can be measured in several minutes rather than most of an hour. Yet even the shorter end is long enough to prevent normal conversational timing and immediate remote control. The changing delay comes from orbital motion. Earth and Mars travel around the Sun at different speeds on different-sized orbits. Their separation therefore expands and contracts across the synodic cycle. When the planets occupy favorable positions on the same general side of the Sun, the path between them is relatively short. As Earth moves ahead and the geometry opens, the path length grows. Near the far side of the cycle, the planets can be separated by a large portion of the solar system. There is no single moment when the delay suddenly changes from short to long. It increases or decreases continuously as the planets move. A mission could begin with one communications rhythm and experience a different one months later. The crew would not live under a permanent 20-minute rule. They would live with a clock whose interval slowly breathes with celestial mechanics. That clock applies to every electromagnetic signal. A spoken message, a medical image, a software update, a navigation instruction, a weather report from Mars, a photograph of Earth, and a warning from Mission Control all travel under the same physical ceiling. Compression may reduce the amount of data. Better antennas may raise reliability. Lasers may increase data rates under suitable conditions. Relays may create alternate routes. None can remove the minimum travel time set by distance. Bandwidth and latency are often confused because both affect communication. Bandwidth describes how much information a link can carry over time. Latency describes how long information takes to begin arriving after it is sent. A wide, high-capacity link could deliver a large file efficiently while still making the first bit wait many minutes to reach Mars. Increasing the width of the information highway does not shorten the highway. This difference matters for future systems. Engineers may send high-resolution video, scientific data, software, and personal messages across a capable interplanetary network. The connection could be rich without being live. Quality can improve. Capacity can grow. The causal delay remains. The same rule governs what an astronaut sees directly. Suppose the one-way light time from Earth to Mars is 12 minutes at a particular stage of the mission. The Earth light entering the observer's eye left 12 minutes earlier. If a cloud system changes, a launch occurs, or lights switch on during that interval, the direct view cannot show the change until new photons arrive. In practice, unaided eyes cannot resolve those details anyway, but the principle remains. Every image of a distant object is an image of its past. Astronomy always works this way. The moon is seen a little over a second in the past. The sun is seen roughly 8 minutes in the past. Distant stars are seen years, centuries, or much longer ago. Mars does not create delayed vision. It makes the delay large enough to enter human relationships and operations. The word now, therefore, becomes local. There is a present moment experienced by the crew on Mars and a present moment experienced by people on Earth, but no message can instantly combine them into one shared exchange. Relativity gives the deeper concept of simultaneity a precise physical meaning, yet no advanced mathematics is needed to understand the practical result. By the time Earth learns what the crew has just done, the crew has already continued living through several more minutes. By the time their reply arrives, both sides have moved further into their own local futures. This does not mean time itself runs 20 minutes slower on Mars. The clocks on both planets continue operating according to their local conditions. The delay belongs to information traveling between locations. Confusing signal travel time with a difference in the rate of time would turn a straightforward communication limit into a false claim. The crew is not frozen while Earth waits, and Earth is not frozen while the crew listens. Both continue. Distance also complicates the meaning of an image marked live. A camera on Earth can capture a scene and transmit it immediately, yet a viewer on Mars receives the data only after the signal crosses the gap. The feed may be live at its source and delayed at its destination. Likewise, Earth can receive a continuous stream from Mars while always watching an earlier state of the mission. Continuous transmission can hide this delay once a stream begins. Frames may arrive without long gaps between them because each follows the previous frame along the same route. The viewer sees smooth motion, but the entire stream remains shifted into the past by the one-way light time plus processing and network delays. Smooth does not mean simultaneous. Robotic Mars missions already operate within this reality. Engineers do not steer a rover as though it were a remote-controlled car beside them. Commands are prepared, checked, transmitted, and executed after the signal arrives. Data describing the result returns later. Greater onboard autonomy allows a spacecraft or rover to handle immediate conditions without waiting for Earth. Human missions will inherit the same physics while adding decisions too complex and personal to reduce entirely to command sequences. The delay can be calculated from a simple relationship. Travel time equals distance divided by signal speed. If the distance doubles, the minimum one-way time doubles. But applying that relationship to an actual mission requires the positions of Earth, Mars, spacecraft, and any relays at that moment. The quoted 3 to more than 20-minute range is therefore a useful summary, not a schedule for every day. Nor is the shortest route always the route a working network can use. Direct communication depends on antennas having suitable geometry and on the signal surviving the environment between transmitter and receiver. A relay may improve coverage while adding a small amount of path length and processing time. Store and forward systems may hold data until the next link becomes available. Practical delivery time can therefore exceed the simple straight-line calculation, sometimes by far more than the added distance alone would suggest. Still, the straight-line light time remains the essential reference. It tells engineers which delays no optimization can remove. If a measured delivery takes longer, part of the excess may be improved through better scheduling, hardware, routing, or software. The interplanetary minimum cannot. Separating those components prevents a fundamental limit from being mistaken for an engineering defect. That minimum also moves predictably, rather than randomly. Navigation teams can calculate it for planned mission dates and update it as trajectories evolve. Clocks can timestamp every transmission, so receivers know when the information was created. Displays can show both local time and source time. These tools help people interpret delayed information correctly, but they also make the separation explicit. Every message carries the age it acquired in transit. Network design adds smaller layers on top of the physical minimum. A message may travel from a habitat to a surface antenna, then to an orbiter, then toward a receiver on Earth, before entering terrestrial networks and reaching its intended person or team. Encoding, error correction, scheduling, retransmission, and processing all take time. These additions can increase practical latency. They cannot reduce it below the light time floor. The distinction becomes especially important when the link is weak or interrupted. Latency means a signal is traveling and will arrive later. A blackout means the signal cannot be transmitted or received reliably through the intended path for some interval. Waiting 20 minutes for a message is not the same as having no usable channel. The effects can occur near the same parts of the orbital cycle, but they are separate problems and require different responses. For now, only latency is needed to change the meaning of home. Earth can be optically visible, the communication network can be functioning, and messages can be moving continuously in both directions. Still, nothing arriving on either planet describes the other planet at that exact receiving moment. Imagine two clocks, one beside the sender and one beside the receiver. When a message leaves Mars, the crew's clock marks the beginning of its journey. Earth's clock continues advancing while the signal crosses space. Reception marks only the end of one path. A response starts a second path while Mars continues advancing. The full exchange is not one shared event. It is a chain of local events connected by light. At the lower end of the delay range, the chain is inconvenient but unmistakable. Several minutes pass before the other side even hears the opening words. At the upper end, a simple question and its fastest possible answer can span a significant part of an hour. Add the time required for a doctor to inspect a scan, an engineer to study telemetry, or a family member to compose a thoughtful reply, and the exchange becomes longer still. Those added human intervals are not failures of the network, they are part of communication. A receiver must understand before responding. Earth may need several specialists to review a technical problem. The crew may be occupied when a personal message arrives. Light time provides the unavoidable minimum. Real life builds on top of it. The result is not silence. Data can flow. Advice can arrive. Relationships can continue. A delay-tolerant network can store information until a path is available and protect it against disruption. Crews can prepare questions with context and send detailed reports. Earth can return carefully assembled guidance. The channel may become one of the most sophisticated communication systems ever built. But sophistication cannot recreate interruption, instant clarification, shared laughter at the same moment, or a warning received before the sender has finished fearing the danger. Those are consequences of timing rather than transmission quality, and their full human meaning belongs to the next stage of the investigation. The physical answer is now clear. The Earth-Mars gap does not merely contain empty kilometers. It contains travel time. Near one part of the cycle, that time may be only a few minutes in each direction. Near another, it can exceed 20 minutes one way. The number changes, but it never reaches zero. Every look toward Earth is therefore a look backward. Every incoming voice began speaking in an earlier Martian moment. Every answer from the crew reaches a world that has continued changing while the message traveled. Distance has become time. Now the question is no longer how long a signal takes. It is what remains of a conversation when neither side can answer the other in the present. What remains is communication without simultaneity. On Earth, conversation depends on more than words. It depends on timing. One person reacts while another is still speaking. A pause can invite reassurance. Confusion can be corrected before it grows. Laughter overlaps. Tone is adjusted after seeing an expression change. Even a telephone call preserves enough immediacy for both people to feel that they occupy the same exchange. Between Earth and Mars, that structure breaks before the content does. Consider the anatomy of a single question without inventing the words. A crew member records or transmits it on Mars. The signal begins crossing space. During the one-way delay, Earth has not yet received anything, although the crew has already moved on to other tasks. When the message arrives, the intended person or team must listen, interpret, decide what response is needed, and prepare it. Only then does the answer begin the return path. Mars continues changing throughout that second journey. At a comparatively short light time, the interval is still too large for natural turn-taking. At the longer end of the range, the physical round trip alone can occupy much of an hour. Add human response time, and one exchange may extend across a substantial part of a work period. A conversation that would take minutes face-to-face can become a sequence distributed across hours. The problem is not simply waiting. Each side must decide what to do while waiting. On an ordinary call, a vague question can be repaired immediately. The listener asks what was meant, and the speaker clarifies. From Mars, ambiguity has a cost, measured in another round trip. A message that omits a measurement, image, timestamp, or piece of context may force Earth either to answer conditionally or request more information. By the time clarification returns, circumstances on Mars may have changed. Communication, therefore, has to become more complete before transmission. A useful technical report may include the observation, relevant data, actions already taken, available options, and the decision deadline. A personal message may carry more context because the receiver cannot ask a quick follow-up. The delay changes not only when people speak, but how they organize thought. This is familiar in a limited way from letters, recorded messages, and email. People have maintained close relationships across oceans, wars, migrations, and long absences without live contact. They learn to write beyond the immediate moment, anticipate questions, and preserve experiences for later sharing. Mars would extend that old human practice through a network of extraordinary technical sophistication. Yet the analogy has boundaries. Historical letters often crossed distances slowly because transportation was slow. An interplanetary message may move at the fastest speed allowed by nature and still arrive late. The delay is not a temporary weakness awaiting a faster courier. It is built into the separation itself. Family contact would therefore resemble correspondence more than a call. Video could retain faces, voices, rooms, celebrations, and daily routines. High bandwidth might preserve excellent image quality, but a recorded smile would not be a reaction to what the crew had just said. It would belong to an earlier moment on Earth, created before the sender knew the crew's latest response. That temporal mismatch can produce small but persistent complications. News may arrive after the crew has already heard part of it through another channel. A family member may answer a concern the crew no longer has. The crew may respond to an emotional moment that has already changed on Earth. Neither side is failing. They are relating across two timelines connected by delayed packets of experience. Design can make those packets more coherent. Messages can be clearly time-stamped. Families can record longer responses instead of trying to imitate a broken live call. Software can group conversations by topic and display the message chain in source time order. Crew members can send short updates frequently or create richer daily journals. None of these choices removes latency, but they can prevent delay from becoming confusion. A family exchange could also carry several layers at once. One recording might answer older messages, describe recent life, and anticipate questions the crew has not yet asked. Attachments could include photographs, ambient sounds, school projects, or ordinary scenes whose value comes from continuity rather than urgency. The crew's reply could do the same from Mars. Instead of sharing one present, both sides would assemble overlapping archives of their lives. This structure creates a responsibility on Earth as well as on the crew. People sending personal news must understand that an astronaut cannot immediately seek clarification, comfort another person, or influence an unfolding event. Information policies cannot eliminate painful realities, but timing, privacy, and available support matter when the recipient is confined millions of kilometers away. The mission must balance honest connection with the operational consequences of news that cannot be answered in real time. The delay can also produce crossed emotional messages. A crew member may transmit concern, then resolve the issue before Earth receives the first recording. Earth may respond with reassurance after a later update is already traveling. Without careful threading, each side can appear emotionally out of step. Timestamps and message context are therefore not administrative details. They help preserve trust by showing which version of events each person knew when speaking. Tone becomes especially important. Text strips away voice and expression. Video carries more context, but may require more data and preparation. A short message written under stress can be interpreted many minutes later without the sender available to correct the reading. Training may therefore include how to communicate emotional state and urgency precisely without creating unnecessary alarm. This does not prove that delay will damage every relationship. Human responses differ, and no crew has lived through the complete Earth-Mars condition. Some people may value the time to compose thoughtful messages. Others may experience the lack of immediate response as painful. The evidence supports the existence of the communication constraint. It does not justify declaring one universal psychological outcome. Mission Control faces the same timing problem with higher operational stakes. Spaceflight on and near Earth has often relied on a close partnership between crews and large teams on the ground. Specialists monitor systems, study telemetry, compare procedures, and advise astronauts. Even when the crew has authority and training, Earth can participate quickly enough to feel present in the decision cycle. Mars preserves the expertise, but removes its immediacy. A technical problem can still be transmitted with detailed sensor data. Engineers on Earth can analyze patterns using facilities and teams unavailable on Mars. They can return diagnostic possibilities, revised procedures, software, or recommendations. This support may be invaluable, but it arrives after the crew has already spent the one-way delay observing, stabilizing the situation, and deciding what cannot wait. The relationship shifts from direct supervision toward delayed consultation. Mission Control cannot continuously guide fine actions through rapid verbal exchange. Instructions must be designed to remain useful when received later. The crew needs authority to act within clearly understood limits, and onboard systems need enough intelligence to support decisions locally. Earth teams must change their own habits. A controller cannot assume that a newly sent correction will reach the crew before the crew acts on an earlier plan. Recommendations need validity windows, assumptions, and conditions under which they should no longer be followed. If new telemetry changes the analysis, the update must identify which previous guidance it replaces. Communication becomes closer to maintaining a carefully versioned body of knowledge than conducting a continuous spoken exchange. The crew, in turn, cannot report only conclusions. Earth's delayed specialists need enough raw evidence to reconstruct why a decision was made. Sensor histories, images, environmental readings, and the sequence of actions can be packaged together. This level of documentation costs time and bandwidth, yet it prevents the consultation from being built on an incomplete picture. Good asynchronous operations depend on sending the reasoning environment, not merely the final question. This shift begins with routine work. Scientific plans may be proposed on Earth, reviewed on Mars, modified by the crew, and returned for later analysis. Maintenance reports may be sent with imagery and data, followed by guidance during a later work cycle. Scheduling must recognize that a question raised near the end of one period may not receive a practical answer until another. The same delay becomes more consequential in medicine. Earth can provide expertise, review scans, compare symptoms, and help plan treatment. But telemedicine cannot behave like a live consultation when each clarification requires another interplanetary crossing. If a condition demands action within minutes, the crew cannot wait for a complete Earth-led diagnostic conversation. This does not mean doctors on Earth become irrelevant. Their knowledge can shape training, medical protocols, onboard decision tools, and supplies long before launch. During the mission, they can still support problems that develop slowly enough for delayed consultation. They may help interpret complex data or monitor recovery over time. The boundary appears when the time available for action is shorter than the communication loop. No invented emergency is needed to understand that boundary. Any system can produce conditions where delay matters. A pressure change, an electrical fault, an unexpected medical symptom, a navigation hazard, or an environmental warning. The documentary does not need to claim that one of these events will occur in a particular way. It only needs to recognize that if immediate action is required, The people and machines on Mars must begin without current guidance from Earth. Decision deadlines make the boundary measurable. If a system can remain stable for hours, Earth may participate deeply in diagnosis. If a choice must be made within minutes, and the one-way delay already exceeds that interval, waiting cannot be the primary plan. The correct response depends on the event, but the communication logic is universal. Support arriving after the deadline can improve later recovery, investigation, or prevention, yet it cannot make the original decision. This forces mission designers to separate reversible from irreversible actions. When time permits, the crew can preserve options while Earth analyzes the evidence. When it does not, procedures must define who decides, which safeguards remain, and how much uncertainty can be accepted. The delay therefore reaches beyond electronics into authority. It determines when responsibility must reside physically with the people exposed to the outcome. That requirement changes preparation. Procedures cannot cover only ideal situations. Crews need principles for diagnosing incomplete information, thresholds for escalating responses, and training across multiple specialties. Equipment must reveal its own state clearly. Medical systems must support local interpretation. Simulations must include delayed help rather than allowing Earth to answer whenever participants become uncertain. Artificial intelligence and onboard software may help organize data, retrieve procedures, compare sensor patterns, and present options. These systems could reduce the number of questions that need to cross space, but describing them as replacements for Earth would overstate what is known. Software can support judgment. Its reliability, training data, verification, and failure modes become part of the mission's risk. The crew itself becomes the immediate network. One member's expertise supports another. Decisions are discussed locally, where answers can still arrive at the speed of speech. This makes crew composition, cross-training, trust, and conflict management operational systems rather than secondary concerns. The nearest human help is not on another continent. It is inside the habitat. Delay also changes urgency signals. On Earth, calling repeatedly can communicate that a situation is worsening. From Mars, multiple messages may already be traveling before the first reaches its destination. Earth could receive a sequence describing several stages of a problem while its first response is still on the way. Both sides need protocols that distinguish updates, corrections, and superseded information. Timestamps become part of meaning. A message saying that a system is stable must identify when that observation was true. A later update may overtake no signal in physical space, but recipients can encounter a backlog or process data in a confusing order if networks reroute information. Clear chronology protects decisions from being based on an earlier state mistaken for the current one. The separation between source time and reception time also affects reassurance. Earth may transmit that help, analysis, or guidance is coming. The crew receives that reassurance minutes later after enduring the interval without it. Mars may report that a problem has been controlled while Earth is still reacting to an earlier alarm. Each side can temporarily inhabit a different emotional version of the same event. Again, this is not silence. The messages exist, and the link may be healthy. The difficulty arises because presence cannot be transmitted whole. Information arrives. Context can arrive. Care can arrive. But none arrives at the moment it was expressed. Crew routines could adapt by treating communication as a continuous, asynchronous workspace. Questions can be queued by priority. Earth teams can prepare responses that anticipate likely follow-ups. Shared records can preserve decisions and rationales. Personal channels can support journals, voice notes, family updates, and private exchanges. The system can be designed around delay rather than treating it as a damaged version of an Earth call. Priorities would need shared definitions. An emergency label cannot make a signal travel faster, but it can determine which data is transmitted first, which Earth team receives an alert, and which prepared resources become available on Mars. Lower priority science or personal traffic may wait, while critical telemetry uses the link. A crew member who marks a message urgent may receive faster processing after it reaches Earth, but not faster physical arrival. Protocols can remove avoidable waiting around the edges. They cannot remove the journey in the middle. For personal communication, priority may mean something different. A message can be emotionally urgent without requiring an operational response. Systems and support teams must preserve privacy while ensuring that crew members have local human support when Earth cannot answer soon. The nearest response to distress will often come from another crew member, even while a message to family is already crossing space. There may even be advantages in some contexts. Deliberate messages can reduce interruption. Teams can document decisions more carefully. Families can send rich collections of ordinary life rather than relying on short-scheduled calls. Crew members can choose when to receive emotionally intense news within operational constraints. These possibilities should not be romanticized, but they show that asynchronous contact is a different medium, not merely a failed one. The human cost comes from what the medium cannot reproduce. An astronaut cannot ask a parent a question and hear hesitation immediately. A mission commander cannot describe a changing problem while an Earth specialist interrupts with a warning based on the last sentence. A doctor cannot guide a physical examination through rapid adjustments. A family cannot share a spontaneous silence in which both sides know they are silent together. Those losses accumulate quietly. They may matter differently on a calm day than during illness, conflict, grief, celebration, or fear. Research on isolation and delayed communication can identify risks and suggest countermeasures, but the complete condition remains untested. No human has combined the distance, duration, confinement, dependence, and point-like view of Earth that a Mars crew would experience. It is therefore safer to describe a transformation than predict a breakdown. Conversation becomes exchange. Mission control becomes delayed expertise. Telemedicine becomes support rather than immediate examination. Family presence becomes recorded continuity. The connection remains real, but its form changes. At the lower end of the light time range, the transformation may feel less severe, yet normal turn-taking is still compromised. At the higher end, attempts to imitate live conversation become impractical. The communication style must evolve continuously as the planets move and the delay changes. This creates a strange contrast with the visible point in the sky. An astronaut may step outside, identify Earth in the twilight, and know that messages are traveling between the worlds. The planet is visible. The network is active, yet neither provides access to Earth's current moment. The point is not abandoned, and neither is the crew. Engineers, doctors, families, and institutions remain involved. The relationship is sustained through preparation, data, recorded expression, and patience. Calling it total isolation would ignore all of that. But calling it conversation would ignore something equally important. Conversation is not only the successful delivery of words, it is a shared rhythm of attention and response. Mars stretches that rhythm until each turn becomes an event of its own. During a mission, the thread can continue in this form. Signals leave, travel, arrive, and receive answers. Then orbital motion carries Earth toward the Sun again. The same geometry that erased the point from the Martian sky begins to affect the radio path. Noise rises. Reliability changes. Mission planners may restrict what is sent or suspend certain transmissions. Delay has not become longer conversation. It is approaching interruption. Interruption begins with the same alignment that removed Earth from sight. As Earth approaches the Sun's direction in the Martian sky, the problem is no longer limited to visible light. Radio signals traveling between the planets must pass close to a powerful and active star. The line of sight may remain geometrically open, yet the channel can become too disturbed for ordinary communication. This period is called solar conjunction. The phrase describes an apparent alignment, not a collision or a permanent barrier. Earth and Mars remain in their own orbits. The Sun lies between them, or close enough to the direct communication path that its environment interferes with the signal. The Sun is not a quiet lamp suspended in empty space. It emits electromagnetic radiation across a broad spectrum and releases a continuous flow of charged particles, known as the solar wind. Its outer atmosphere extends far beyond the visible surface. Magnetic fields and plasma structures change with solar activity. A radio wave passing through this environment can be weakened, delayed slightly, scattered, or distorted. To a receiver, the effect can resemble trying to detect a precise voice beside an immense source of noise. The comparison is incomplete because solar interference is not ordinary sound, and modern receivers use sophisticated encoding, antennas, and error correction. But the practical problem is similar. The desired signal becomes harder to separate from the environment surrounding it. The closer the radio path appears to pass to the Sun, the more difficult reliable communication can become. Signals may contain errors. Data packets may need retransmission. Navigation measurements can become less precise. A command altered by corrupted data could be worse than no command at all, especially when it controls a spacecraft or surface system millions of kilometers away. Plasma matters because charged particles influence the propagation of radio waves. The effect depends on signal frequency and on the changing density of material along the path. Instead of adding one simple delay, the solar environment can introduce fluctuations that complicate tracking and decoding. Engineers can measure and model some of these effects, but the link margin narrows as the geometry becomes unfavorable. Navigation is part of the same problem. Deep space teams estimate position and motion using carefully timed radio signals and other measurements. Disturbance along the path can reduce confidence in those estimates. A crewed mission would not suddenly forget where Mars is, but precise navigation and timing services still need robust alternatives and conservative operating rules during degraded conditions. Error correction can recover data when enough of the signal survives. Information is encoded with redundancy, so a receiver can identify or repair certain errors. Lowering the data rate can give the link more margin. Repeating a packet can replace corrupted content. These methods make communication resilient, yet each has limits. When interference becomes too severe, sending more consequential data can increase uncertainty rather than reduce it. For that reason, mission teams do not simply continue sending every command until the link fails completely. They can deliberately reduce or suspend commanding during the most difficult period. A planned communications blackout may therefore reflect caution rather than absolute physical impossibility. The network is treated as unreliable enough that transmitting consequential instructions creates unacceptable risk. This is why the word blackout needs qualification. In one context, it can mean no usable direct communication. In another, it can mean operations have chosen not to send certain commands while limited telemetry continues. Different frequencies, antennas, data rates, coding schemes, spacecraft geometries, and mission rules can produce different thresholds. There is no single conjunction blackout duration that applies identically to every Mars mission. NASA trajectory and communication studies examine these periods for specific crewed mission concepts. Their modeled disruptions can extend through parts of several weeks, but the exact interval depends on the trajectory, the acceptable angular separation from the Sun, the link architecture, and the operational definition of usable communication. A number from one concept should not be presented as a universal calendar for the first crew. The transition into disruption is usually gradual. The link does not have to switch from perfect to silent in one instant. Data rates may be reduced. Commands may become more conservative. Engineers may rely on stronger error correction or postpone non-essential transmissions. As the apparent separation narrows, mission rules can impose increasing restrictions until the highest risk interval has passed. That progression can be organized into operational phases. During an early phase, the network may still carry normal traffic while teams monitor link quality more closely. A later phase may limit commanding, reduce data volume, or require additional verification. At the most restrictive point, the mission may avoid transmitting commands through the affected route. As conditions improve, those steps can be reversed only after tests show that the link is trustworthy. Phases prevent a vague idea of bad communication from controlling decisions. Every restriction can be tied to measurable conditions and predefined rules. The crew knows which services remain available. Earth knows what information can still be expected. If the link behaves differently from predictions, both sides have fallback procedures prepared before they lose the ability to coordinate them. The design must also account for messages already in transit when a restriction begins. A command sent under acceptable conditions may arrive after the environment has changed. Timestamps, validity windows, and acknowledgements help determine whether it should still be executed. In interplanetary operations, information can become outdated while physically traveling toward its destination. The return can also be gradual. As orbital motion widens the path from the Sun, teams can test the link, restore limited commanding, verify spacecraft state, and then resume normal operations. Reconnection is a process rather than a dramatic switch. Both sides must confirm which data and decisions were exchanged before the disruption and what changed during it. Robotic Mars missions already prepare for this environment. Before conjunction, teams send instructions designed to keep orbiters, landers, and rovers safe, while direct commanding is limited. The machines may continue routine activities, collect data, monitor their health, and store information for later transmission. They are not necessarily inactive. They operate within carefully bounded autonomy. A human crew would require a far more capable version of that preparation. People cannot be placed into a simple safe mode for weeks. They must maintain life support systems, monitor power, manage consumables, respond to weather and equipment changes, conduct medical care, and make decisions whose timing cannot be postponed until Earth returns. The communication interruption would not create autonomy from nothing. It would expose how much autonomy the mission already possessed. Preparation would begin before the channel degraded. Earth could transmit updated procedures, forecasts, software, medical guidance, maintenance priorities, and decision frameworks. The crew could review unresolved questions and request information while the link remained dependable. Non-essential activities carrying unusual risk might be rescheduled. Systems could be placed in stable configurations with known margins. Both sides would also establish what silence means. The absence of a message should not automatically indicate disaster if the disruption is expected. Schedules, link tests, fallback paths, and predefined thresholds can distinguish planned loss of contact from evidence of a technical failure. Predictability removes some uncertainty, but it does not restore communication. This shared expectation protects both operations and people. Earth teams do not repeatedly transmit into an unusable path merely because no acknowledgement arrives. The crew does not interpret every missing update as evidence that something has happened on Earth. Silence becomes a known state with a beginning, expected limits, and a recovery plan. It remains separation, but not unexplained disappearance. Contingency rules must cover the possibility that contact does not return on schedule. The first response may involve checking local equipment, switching antennas, testing a relay, or changing data rates rather than assuming a crisis on the other planet. Each step takes time because status information itself is delayed. Recovery procedures need patience built into their logic. During the most restricted interval, the crew would rely on local records and tools. Engineering databases, medical references, simulation models, spare part inventories, and decision support would need to be available without querying Earth. Procedures would have to include branches for conditions that mission planners could foresee, while crew training would cover situations that cannot be reduced to a script. This does not imply that every conjunction produces total isolation from every possible path. Communication architecture matters. Mars orbiters can relay between surface assets and Earth. Future systems might use additional spacecraft positioned to create alternate routes, including concepts that place relays away from the direct Sun-Earth-Mars line. Optical communication and different radio links may offer different capabilities and constraints. Surface coverage is another link in the chain. A habitat may communicate through an orbiter because Earth is below its local horizon, or because a direct antenna lacks sufficient performance. If the orbiter-Earth leg is degraded, a healthy surface-to-orbiter connection cannot complete the route. Conversely, a strong interplanetary link is useless to the crew if local equipment cannot reach it. Conjunction planning must test the network end-to-end, from a person or sensor on Mars through every relay and ground station to the intended recipient on Earth. But a relay does not abolish physics merely by adding another antenna. Its location must provide a path that avoids the worst interference, and the signal still needs sufficient power, pointing accuracy, availability, and capacity. The relay becomes another critical system that can fail or require maintenance. Alternate routes can mitigate disruption. Describing them as guaranteed elimination would exceed the evidence. A useful alternate route must bend the network around the dangerous geometry by placing a functioning node where both legs remain available. That can require spacecraft far from the direct Earth-Mars line, long-lived power and propulsion, precise navigation, compatible communications hardware, and enough capacity for crew-critical traffic. Building the route means launching and maintaining infrastructure before relying on it. Redundancy also creates choices. If several paths remain available, the network can reserve the most robust one for essential telemetry, health information, and emergency messages, while lower priority data waits. scientific archives, and personal media can be stored locally. This does not prevent emotional separation, but it can preserve a thin operational thread that a simpler architecture would lose. Any claim that a particular relay arrangement solves conjunction permanently must therefore wait for a defined architecture and analysis. The relevant question is not whether a relay can be drawn on a diagram, it is whether the complete chain can meet crew safety requirements throughout the actual trajectory, with failures, maintenance needs, and solar conditions included. Optical links present their own trade-offs. Lasers can support high data rates and narrow beams, but they demand precise pointing and remain sensitive to geometry, atmospheric conditions at terminals, and obstruction by the sun's direction. A technology that improves capacity under ordinary conditions may not solve every conjunction scenario. Mission design must evaluate the complete network rather than assume one new link removes the problem. Store and forward communication can protect data when a continuous route is unavailable. Messages are held at a spacecraft or network node until the next link opens. This prevents information from being lost merely because the path is temporarily broken. It is valuable for scientific files, personal messages, and non-urgent reports. It cannot deliver time-critical help during the interval when no route exists. The distinction between delayed and disrupted communication now becomes unavoidable. Latency means the message is on its way. Conjunction disruption may mean the message cannot begin or complete the journey through the intended route. Under latency, both sides can estimate when an answer might arrive. Under a blackout, the answer may have to wait until the channel itself is restored. That changes the psychology of waiting, without allowing a confident prediction of harm. A crew that knows a reply is traveling experiences a different condition from a crew that knows no reply can yet be sent. Training, trust, and clear schedules may make the period manageable. Individual responses will differ. No human has experienced a full solar conjunction interval from the Martian surface. Operationally, the difference is concrete. Earth cannot monitor every development as it occurs. The crew cannot send a new question whenever a procedure reaches an unexpected branch. Mission Control cannot update recommendations using the latest surface data. Decisions accumulate locally, and Earth learns their sequence later. Reconnection, therefore, requires more than exchanging greetings. The crew must transfer records describing system changes, medical events, scientific observations, maintenance actions, and decisions made during the restricted period. Earth teams must compare that new state with the assumptions embedded in guidance prepared before conjunction. Old instructions may no longer apply. Chronology becomes crucial. A backlog of messages can contain information created at different moments under different conditions. Every record needs source time, version, and context. Automated systems can help organize the exchange, but human teams still have to determine which facts remain current and which have been superseded. The first message after disruption may not be the most important one. Critical telemetry could receive priority. Network capacity may be restored in stages. Earth may first need to confirm that the crew and essential systems are safe, then retrieve detailed records, then resume lower priority science and personal traffic. Reconnection has an operational order. The Sun has therefore not created an impenetrable wall. It has created a region where communication risk rises enough to alter behavior. The strongest response may be temporary suspension of direct commanding, but the exact form depends on the mission. Treating every conjunction as absolute silence would be as misleading as claiming there is no problem because a weak signal might remain detectable. The most credible description lies between those extremes. Communication can degrade severely. Certain transmissions may be restricted. Direct links may become unusable for a planned interval. Alternative paths may reduce the impact if the mission architecture provides them. Earth and Mars eventually move into a more favorable geometry, allowing the channel to recover. For a crew, this is scheduled separation created by orbital mechanics. The dates can be predicted. Procedures can be rehearsed. Supplies and information can be positioned in advance. Everyone can know that contact should return. Still, prediction does not make the interval empty of consequence. A known storm can be prepared for and remain dangerous. A planned night still becomes dark. During conjunction, the crew continues living on another planet, while Earth's ability to participate is reduced to whatever the surviving architecture permits. The event also reveals a deeper truth about a Mars mission. Communication cannot be treated as a continuous external service on which every decision depends. Even outside conjunction, delay limits Earth's role. During conjunction, disruption makes that limitation explicit. The mission must remain coherent when the channel narrows or closes. That requirement reaches backward into vehicle design, crew training, medical planning, software, governance, and mission rules. Autonomy is not an optional feature added for convenience. It is a response to a predictable feature of the solar system. When the sun moves away from the radio path, the thread can be restored. Messages cross again. Earth receives the history of the interval. The crew receives news and guidance prepared beyond Mars. The blackout, like the optical disappearance, ends. But its significance depends on scale. An interruption lasting days or weeks means one thing inside a short visit and another inside a mission lasting years. The crew's exposure to delay, conjunction, and autonomy is determined by the path chosen to Mars and the path available home. The next question is therefore not whether communication returns. It is how long the first humans must build their lives around its absence in practice. How long depends on a fact no engine can negotiate. Mars does not remain beside Earth. The two planets are continually moving around the Sun. A spacecraft cannot leave at any convenient date, travel outward, and expect the return path to remain unchanged. By the time a crew reaches Mars, Earth has advanced along its orbit. By the time the crew is ready to depart, both worlds may occupy a geometry that makes a direct, practical return far more demanding than the outward journey. This is why human Mars missions are designed around launch opportunities rather than ordinary schedules. Favorable opportunities recur on the same broad 26-month rhythm that changes Earth's position in the Martian sky. Mission planners choose trajectories that meet moving planets while balancing travel time, propulsion, mass, energy, exposure, and the ability to return. The first humans may therefore spend only part of their absence on Mars. The mission also includes the outbound transit, time waiting or working near the planet, and the journey back. A surface stay measured in weeks can belong to a total mission measured in years. That distinction immediately corrects another assumption hidden inside the title. A first landing does not automatically mean permanent settlement. Current architecture studies include missions designed to bring crews home. Other visions imagine longer-term settlement, but they should not be blended with every initial exploration concept. Whether a particular crew returns is a decision built into its mission architecture, not an unavoidable consequence of reaching Mars. Broadly, Mars mission studies often compare two families of trajectories. One favors longer stays near Mars and uses relatively efficient transfers aligned with favorable planetary geometry. The other accepts higher energy, different routing, or a more complex return in order to shorten the surface stay or total exposure under selected assumptions. They are commonly described as conjunction class and opposition class, though individual studies use definitions and variants that must be read carefully. The names can be misleading if treated as simple promises. A conjunction class mission is not defined merely by experiencing solar conjunction, and an opposition class mission does not avoid every communication problem. The categories describe trajectory strategies shaped by planetary positions and energy. Their operational details depend on propulsion, staging, mission goals, and the architecture being studied. In a long stay or conjunction class pattern, the crew may spend roughly 6 to 9 months traveling outward, remain near or on Mars for many months, and then make a comparable journey home. Some planning ranges place the stay at several hundred sols. A sol, the Martian solar day, is about 40 minutes longer than an Earth day. Hundreds of sols therefore represent a sustained chapter of human life, not an extended visit resembling an expedition of a few weeks. The long stay is not chosen because mission planners simply want the crew to wait. It can allow the planets to move back toward a return geometry that demands less energy than leaving immediately after arrival. Orbital mechanics turns patience into part of the transportation system. The crew remains, while the destination they need to meet moves into a more favorable position. Energy in this context does not mean electricity consumed by the habitat. It refers largely to the changes in velocity that spacecraft propulsion must provide to depart one path, enter another, and meet a moving world. Every additional requirement influences propellant, vehicle mass, staging, and margins. A trajectory that looks shorter on a calendar may demand a transportation system with very different capabilities. This is why waiting can be cheaper in propulsion while expensive in everything needed to keep humans alive. A long stay reduces pressure to force an immediate return geometry, but it requires a surface system that survives the interval. Food, power, maintenance, radiation protection, medical capability, and replacement parts become part of the price paid for orbital efficiency. Mission architecture trades one constrained resource against another. The crew's time is also a resource. A long mission must preserve health, attention, and useful work across repeated routines. The surface program cannot be planned as a continuous sequence of dramatic expeditions. Equipment maintenance, habitat care, exercise, medical monitoring, communication, rest, and contingency margin consume much of the calendar. Hundreds of sols create scientific opportunity only if the human system remains functional enough to use them. That patience has benefits. More surface time can support broader science, repeated exploration, maintenance experience, seasonal observation, and better use of equipment that was expensive to send. A crew that has crossed interplanetary space gains enough time to do more than plant instruments and leave. It also multiplies exposure. Every additional month extends dependence on life support, surface power, food, spare parts, medical capability, crew cohesion, and communication across delay. Conjunction may occur during the mission, depending on dates and trajectory. Dust seasons and environmental changes can become operational concerns. A longer stay gives time for mastery, while giving systems more time to fail. The shorter stay family pursues a different compromise. Some NASA planning concepts have examined surface stays around 30 sols within total missions still lasting roughly 2 years or more. The exact numbers are scenario-dependent. Examples in architecture studies are not approved schedules for the first landing. They show that a brief presence on the surface does not produce a brief separation from Earth. 30 sols would impose its own intensity. The crew would need to check out surface systems, adapt to Martian gravity after months in transit, begin planned science, maintain the habitat, prepare samples or equipment, and ready the ascent sequence within a narrow interval. Weather or equipment delays would consume a larger fraction of the available stay. Less time on Mars can mean less time to recover from disruption. The short stay also places greater weight on assets delivered in advance. Habitats, power, ascent systems, communications equipment, and surface supplies would need confirmation before the crew commits to landing. If the mission depends on a tightly timed departure, the return system must remain ready on that schedule. Reducing residence time does not reduce the need for reliability. It can reduce the time available to repair or improvise. From the perspective of Earth disconnect, the short surface phase may be misleading. The crew has already watched Earth shrink throughout the outbound journey and adapted to increasing latency before touching Mars. It then departs for another long transit, rather than stepping immediately back into Earth's environment. The Martian stay is brief, but interplanetary separation surrounds it on both sides. To leave Mars sooner, the crew may need a higher energy trajectory, a return path that changes the mission's geometry, or additional time traveling through space rather than waiting on the surface. Some opposition-class concepts include a passage influenced by Venus or other trajectory features. These options can increase propulsion demands, speed, thermal constraints, radiation considerations, or mission complexity. Shorter surface time can exchange one kind of exposure for another. The contrast is therefore not simply long mission versus short mission. It is a distribution of time and risk. One architecture may place more time on Mars and use more favorable transfer energy. Another may reduce surface operations while increasing transit demands or total system complexity. Both still require a crew to leave ordinary Earth communication behind. A 30-sol stay could feel short when compared with hundreds of sols, yet the astronauts may already have spent months in transit before landing. They may face another long journey after departure. The surface visit is only the central event in a timeline that begins at launch and ends after Earth return and recovery. Likewise, a long-stay mission is not equivalent to permanent emigration. The crew can remain on Mars for more than a year and still depart on a planned return vehicle. Long enough to transform daily life and forever are not the same claim. Mission duration also determines how the communication delay evolves. Because Earth and Mars move throughout the journey, the one-way light time changes during transit, surface operations, and return. The crew may experience relatively shorter delays during one phase and much longer delays during another. Communication protocols must adapt rather than assume one constant interval. The same is true of solar conjunction. Whether it occurs during transit, during a surface stay, or outside the crewed portion depends on mission dates and trajectory. A long mission has more opportunity to encounter unfavorable geometry, but no conclusion should be drawn without modeling the actual timeline. Architecture studies calculate disruption windows for precisely this reason. Two missions landing at similar places could therefore experience different communication histories because they depart in different windows or follow different paths. One crew might encounter its most difficult geometry while still in transit. Another might face it during a long surface residence. The engineering problem is not attached permanently to Mars itself. It belongs to the evolving arrangement among the mission, Earth, Mars, and the Sun. This is why a source describing one trajectory cannot automatically establish the blackout dates, maximum delay, or surface exposure for another. The timeline must be calculated as a system. Duration turns each communications constraint into accumulated experience. One delayed family exchange may be manageable. Months of asynchronous contact establish a new routine. One period of reduced commanding may be a planned operational event. Years in which Earth can never provide immediate help reshape the mission's authority from the beginning. The crew's relationship with Earth can also change across phases. During outbound travel, Mars grows from destination into nearby world, while Earth recedes. On the surface, the habitat and local landscape become the crew's immediate environment. During return, Earth grows closer and the delay contracts, but the astronauts remain inside the mission until landing. Reconnection is gradual before it becomes physical. These phases matter because isolation is not uniform. Transit confinement differs from surface confinement. On Mars, the crew can perform exploration and inhabit a planetary landscape, yet remains dependent on a sealed system. During travel, the external environment and operational tasks differ. A single number for total mission days cannot capture every human condition inside it. Outbound travel contains anticipation and increasing distance. Surface residence adds planetary day-night cycles, gravity, dust, external work, and a fixed landscape. Return travel reverses the destination, but not instantly the conditions. The crew is still confined, delayed, and far from rescue for months. The same people may experience each phase differently, even though the total mission is described by one duration. Communication follows those phase changes. Antenna geometry and available relays may differ between a transit vehicle and a surface base. Work schedules change. The volume and kind of data change. On Mars, scientific imagery and habitat telemetry may dominate. During transit, vehicle health and navigation may take priority. Personal messages continue through all phases, but the routines for sending and receiving them may evolve. Return creates an important psychological boundary without guaranteeing an immediate return to normal life. As the light time contracts, exchanges can become faster, yet ordinary conversation remains impossible until the delay is sufficiently small and network conditions permit it. Earth grows from a point, but recovery, reintegration, and the meaning of the experience lie beyond what mission duration calculations alone can predict. Architecture also determines what must be delivered before the crew. A long surface stay requires consumables, spare parts, power systems, habitats, mobility, ascent capability, and contingency reserves sized for the planned interval. A short stay may reduce some surface needs, but demand a different propulsion and vehicle arrangement. Communication autonomy cannot be separated from logistics. Local decision-making is useful only if the crew has tools and resources to act. Return plans add another meaning to the word home. A crew may know that Earth is the mission's destination and still be unable to leave Mars until the orbital window opens. Mechanical readiness is necessary, but not sufficient. The ascent vehicle can be prepared, the crew can be willing, and Earth can be waiting, while celestial geometry sets the practical departure schedule. This waiting is not absolute imprisonment. It is the consequence of choosing trajectories within available energy and system capability. More propulsion or different technologies can expand options, but every alternative carries mass, risk, development, and reliability costs. No realistic architecture turns interplanetary travel into an airline timetable. Future propulsion could alter transfer times and mission designs. Nuclear thermal systems, advanced electric propulsion, or other technologies may change the balance among mass, duration, and energy if developed and adopted. They should not be treated as guaranteed features of the first mission. The scientifically responsible outline must distinguish a current planning example from a future possibility. The same caution applies to commercial settlement proposals. A company may describe a long-term goal of building a permanent population on Mars. That ambition does not prove that the first people to land will be unable or unwilling to return. Exploration, base construction, and settlement are different mission categories. Their crews may share the same sky and light time delay while living under very different commitments. What can be said with confidence is narrower. Any credible round-trip mission must follow changing planetary geometry. Transit takes months under conventional planning assumptions. Total absence can extend roughly 2 to 3 years in studied concepts. Surface stays can vary from around a month in some short-stay studies to hundreds of sols in long-stay designs. The final first mission timeline remains undecided. That uncertainty does not weaken the central conclusion. Every serious option lasts long enough for delay to become normal rather than exceptional. Even a comparatively short surface campaign cannot rely on uninterrupted real-time direction from Earth. The crew must arrive already capable of operating through latency, local emergencies, and any planned communication disruption in its timeline. The long-stay path gives that autonomy more time to mature and more opportunities to be tested. The short-stay path compresses surface objectives and may make each sol more operationally dense. One spreads decisions across a long residence. The other can concentrate them into a narrow window. Neither returns mission control to the room. This is the shared condition beneath competing architectures. Propulsion can change where the crew spends its time. Trajectory design can move risk between transit and surface operations. Additional infrastructure can improve communication and logistics. But while humans remain at Mars' distance, Earth is an advisor whose knowledge arrives later. The first crew will therefore not be separated for one dramatic moment. Separation becomes a calendar. It is measured in launch windows, transit months, surface sols, conjunction phases, maintenance cycles, delayed birthdays, and the long arc toward a return opportunity. Whether the mission lasts closer to 2 years, approaches 3, or follows a different future design, the important change occurs early. The crew cannot wait until Mars to learn independence. Autonomy has to exist before departure, be practiced during transit, and remain available through every surface phase. Mission architecture can answer when the crew leaves, how long it stays, and when it may return. It cannot answer every decision that will arise while Earth is minutes away by light. That responsibility has to move with the astronauts. Responsibility cannot travel later. It has to be present when the decision is made. For crews operating close to Earth, mission control can participate in events while they unfold. Specialists monitor data, compare procedures, and respond quickly enough to influence the next action. The astronaut and the ground team remain separated by distance, but they can still occupy almost the same operational moment. At Mars, that relationship becomes impossible. Earth does not lose its expertise. Mission control may still contain larger teams, deeper databases, specialized laboratories, powerful computers, and decades of institutional knowledge. What it loses is the ability to place that expertise inside every immediate decision. Advice remains valuable, but arrival time determines which problems it can solve. The change is best understood as a transfer of authority rather than a loss of support. Earth can prepare, advise, review, and learn. The crew must observe, stabilize, choose, and act locally whenever waiting would make the outcome worse. Mission control becomes a delayed partner. Mars becomes the place where consequences occur first. That transfer begins with the machines. A system designed for Mars cannot merely report that something has failed. It must help the crew understand what changed, which functions remain available, what secondary effects may follow, and which actions are safe. Reliability includes the ability to diagnose a problem when the engineers who designed the hardware cannot join the investigation in real time. Sensors need to reveal more than a single warning light. They may track trends, compare redundant measurements, record event histories, and show how one subsystem influences another. Clear interfaces matter because a crew under pressure cannot spend an interplanetary round trip discovering what a code means. Documentation and diagnostic tools must live with the equipment. The system should also fail in understandable ways. Redundancy is useful only if the crew can identify which channel is trustworthy. Automatic protection is useful only if people can determine what it did and why. A machine that silently changes state may preserve itself while leaving the operators uncertain about the habitat it supports. Diagnosability begins before failure. Systems can record baseline behavior so the crew recognizes slow drift rather than waiting for an alarm. Components can be arranged for inspection and replacement instead of sealed behind inaccessible structures. Connectors, tools, labels, software versions, and spare parts can be standardized where practical. These choices may appear ordinary, but they determine whether people can convert a warning into a repair without an expert standing beside them. Training must reflect the real interface. Memorizing a nominal checklist is not enough if the display presents conflicting data or if a failed component makes the checklist impossible to follow. Crews need experience with incomplete symptoms, false indications, cascading effects, and several plausible diagnoses. The purpose is not to teach them to guess. It is to teach them how to preserve evidence, test assumptions, and avoid making an uncertain problem irreversible. Earth's engineers can contribute by designing procedures as conversations that have already happened. A well-built guide explains what evidence justifies each branch, what results should appear after an action, and what condition requires stopping. It allows the distant specialist's reasoning to travel before the emergency exists. Static instructions then become part of a larger local decision system. Onboard software can organize evidence, retrieve procedures, simulate options, and highlight inconsistent readings. It may help the crew distinguish a faulty sensor from a real environmental change. More advanced decision support could compare current data with modeled failure patterns. But autonomy is not the same as surrendering judgment to an algorithm. Software can be wrong because its sensors are wrong, its model is incomplete, its assumptions no longer apply, or the event lies outside its training and validation. The crew needs ways to inspect recommendations and understand confidence. Mission control can later audit the reasoning, but the immediate users must decide whether to trust it. Maintenance follows the same principle. Earth can transmit a detailed repair plan after reviewing images and telemetry. If the equipment can remain stable, waiting may be the safest choice. If a condition is deteriorating, the crew needs local procedures, tools, spare parts, and authority to begin. Delayed expertise works best when the system gives people enough time to use it. This creates a design objective rarely visible in dramatic depictions of Mars: preserve decision time. A habitat can be built with isolation valves, reserve capacity, graceful degradation, and independent backups that slow the development of a problem. Those features do not eliminate failure. They create an interval in which diagnosis, communication, and deliberate action remain possible. Time is therefore a safety resource. A reserve of oxygen, power, water, cooling, or data can matter not only because the resource is useful, but because it prevents an immediate choice from becoming irreversible. The more time a system can provide, the more opportunity Earth has to contribute. When no time remains, the architecture has already transferred the decision to Mars. Navigation and surface operations require similar independence. A crew exploring beyond the habitat cannot assume that Earth will approve every route adjustment or react instantly to terrain. Local maps, positioning systems, vehicle sensors, weather observations, and return margins must support decisions where they occur. Earth can help plan an expedition and analyze results later. It cannot drive from another planet through light time delay. Scientific work also changes. Mission teams on Earth may define broad priorities and examine transmitted data, but the crew encounters conditions first. An unexpected outcrop, instrument behavior, dust event, or limited work window can require immediate judgment about what to sample, what to postpone, and when to return. Autonomy allows science to respond to Mars rather than forcing Mars to wait for a reply. This does not free the crew from mission goals. Authority works inside agreed boundaries. Objectives, safety rules, ethical standards, resource limits, and protected systems can be established before launch. The challenge is to define those boundaries broadly enough for adaptation and clearly enough to prevent confusion when Earth is unavailable. Medicine makes the transfer especially visible. A Mars crew may have access to medical instruments, supplies, decision aids, and training designed for likely conditions. Doctors on Earth can review data and offer expertise whenever time permits. Yet no communications architecture can place an Earth physician's hands inside the habitat. Examination, immediate treatment, monitoring, and procedural action belong to people and systems on site. The necessary capability depends on the medical event, crew composition, mission duration, and available equipment. It would be irresponsible to claim that every illness can be handled locally or that every emergency becomes fatal. The accurate conclusion is structural. Conditions requiring action sooner than the communication loop cannot depend on a complete Earth-led consultation. Cross-training becomes essential because a small crew cannot carry a full hospital, engineering center, laboratory, and flight control organization in separate specialists. Members may have primary roles while learning enough outside them to support one another. The best qualified person can also become the patient, so procedures and tools cannot assume that one expert is always available. Medical privacy adds another layer. Health information may need transmission to Earth, but the crew also lives and works inside a small social system. Rules must define who can access sensitive data, when safety overrides privacy, and how delayed advice is incorporated into local decisions. Distance does not remove ethics. It forces ethical judgment to operate without immediate institutional supervision. The same is true of interpersonal conflict and governance. A Mars crew cannot send every disagreement to managers on Earth and wait for a ruling. Routine tensions need local resolution. Work assignments, resource use, fatigue, privacy, and risk acceptance may require decisions affecting everyone in the habitat. A chain of command can clarify authority, but authority alone does not create trust. Governance must anticipate situations where information is incomplete and Earth's response will arrive late. Which decisions require group consultation? Which belong to a commander, medical officer, or system specialist? When can an individual refuse an unsafe task? How are dissent and uncertainty recorded for later review? These are operational questions, because conflict can influence safety as directly as equipment. Authority may also shift with the problem. A commander can coordinate the mission, while a medical officer controls clinical decisions and an engineer controls access to a hazardous system. Predefined roles prevent every disagreement from becoming a contest of rank. They also establish when one domain affects another strongly enough to require a broader decision. Rules need an emergency path and a recovery path. Temporary authority used to stabilize a crisis should not quietly become permanent control after the immediate danger passes. Records, crew review, and eventual Earth consultation can restore normal governance. This matters because an isolated group cannot afford uncertainty about whether extraordinary decisions remain in force. Clear endings are as important as clear triggers. They make conflict discussable before distance and pressure magnify it. Earth still matters in accountability. Decisions can be documented and reviewed. Mission rules can define responsibilities. Delayed consultation can help resolve issues that are not urgent. But oversight occurring later cannot replace judgment required now. The crew must carry both authority and the knowledge that its choices will eventually be examined. That combination can feel different from simple independence. Autonomy is often described as freedom, yet on Mars it is also burden. The crew gains the power to act, because no one else can act soon enough. Every local decision contains the possibility that Earth, with more information and time, might later recommend something different. Preparation can reduce this burden by aligning decision principles before launch. Earth teams and crews can rehearse delayed scenarios, identify thresholds for local action, and practice sending complete evidence packages. Simulations can force participants to continue without immediate rescue from an instructor. The goal is not to predict every event, but to build a shared logic that survives uncertainty. That shared logic must survive fatigue. A decision process that works only when everyone is rested and calm is not robust enough for a long mission. Checklists, cross-checks, protected rest, workload limits, and clear handovers help prevent autonomy from becoming impulsive action. Human performance is part of the system margin. Teams also need methods for recognizing when confidence is unjustified. Expertise can become dangerous if a crew member feels pressure to produce certainty where none exists. A structured pause, independent review, or challenge from another specialist can expose assumptions before action. Authority should make decisions possible, not make questions unwelcome. Earth can support this culture through delayed review that is honest rather than punitive. If crews hide uncertainty because every deviation will be judged later, mission control receives worse information. Documentation should enable learning and accountability, while recognizing that local decisions were made under different time, evidence, and risk conditions from the later analysis. Procedures should distinguish between immediate stabilization and permanent repair. The crew may first place a system into a safe condition, preserving options while Earth analyzes the data. Later guidance can support a more complex intervention. This division uses local speed and distant expertise together rather than treating them as competitors. The same layered approach applies to decisions. Some actions can be taken automatically within preset limits. Others require crew judgment. Still others can wait for Earth. A resilient mission knows which category a problem belongs to and can change categories if conditions worsen. Communication must support that structure. Reports should state not only what happened, but what has already been done, which assumptions guided the action, what deadlines remain, and what help is requested. Earth's response should identify the data on which it relies and the conditions under which its advice remains valid. Both sides need to recognize that the situation may change while the message travels. Supply chains impose another form of autonomy. A replacement part cannot arrive in minutes or days merely because Earth understands the failure. Depending on mission timing and transport capability, resupply may be unavailable for a long period. The crew needs repair methods, compatible components, fabrication capability where practical, and strategies for using limited inventory. Pre-positioned cargo reduces dependence only if it arrives safely, remains functional, and can be accessed when needed. A spare stored at another site may require mobility and favorable conditions. A component exposed to years of storage may need testing before use. Logistics on Mars is therefore not simply a list of objects delivered from Earth. It is a network of condition, location, compatibility, and remaining life. Fabrication can widen options, but has boundaries. Producing a bracket or tool does not imply that a crew can manufacture every pump, sensor, seal, medicine, or electronic component. Raw material, energy, machine capability, quality control, and design files constrain what can be made. The strongest plan combines repairable hardware, carefully selected spares, limited fabrication, and procedures for operating safely with reduced capability. Inventory is therefore knowledge as well as material. The crew must know what exists, where it is stored, what can substitute for something else, and which resource cannot be consumed without threatening a later phase. Earth can help model options, but the physical constraints are local. Power, air, water, food, thermal control, communications, and mobility are connected. Saving one system by consuming another resource may transfer rather than solve the risk. Decision tools need to reveal these relationships. A repair that appears successful in isolation can be unacceptable if it removes the margin needed for return. This interconnectedness makes authority collective even when one person has command. Engineers, medical specialists, scientists, and operators see different consequences. Local discussion can combine those views immediately. Earth adds depth later. The most capable system is not a lone heroic astronaut, but a crew able to reason together with transparent machines and delayed partners. Heroic improvisation may produce compelling fiction, but it is a poor architecture. A real mission should not depend on extraordinary luck or one person discovering an impossible solution. It should create margins, tools, training, and decision structures that make competent adaptation possible. This is the operational meaning of being beyond immediate help. It does not mean no help exists. Earth can provide enormous assistance before, during, and after an event. It means help cannot always arrive before action becomes necessary. The crew becomes the first responder, local mission control, maintenance team, medical team, and government of a tiny human world. Earth remains connected, informed, and influential, but not physically present in the decision interval. Distance has transferred authority outward. Engineering can describe what that authority requires. Procedures can define it. Simulations can rehearse it. Yet none of those tools can determine how the first humans will feel when they realize that every immediate answer must come from inside the habitat. Autonomy may feel like competence. It may feel like responsibility. At times, it may feel like abandonment, even when Earth is listening and a reply is already on its way. The machines can be designed for distance. The unresolved question is whether the human mind can be prepared for what that distance means. Human beings have never looked at Earth from the place Mars will create. Astronauts have seen the planet from orbit, where it curves beneath them and fills much of their view. Apollo crews traveled far enough to see Earth as a complete sphere suspended in darkness. Those perspectives were physically distant from ordinary life, yet Earth remained visually rich, recognizable, and close enough for rapid radio exchange. Mars changes the combination. From its surface, Earth becomes point-like to unaided vision. Communication takes minutes in each direction and may be disrupted near conjunction. Immediate help resides with the crew. The planet remains real and connected, but it is no longer a surrounding environment, a detailed globe, or a participant in the present moment. Space psychologists have proposed that this condition may produce an experience sometimes called Earth out of view or Earth disconnect. The term does not name a proven disorder with a known rate, diagnosis, or inevitable outcome. It identifies a potential stressor, the psychological effect of living where Earth is visually insignificant and real-time contact with it is impossible. To understand why that possibility attracts attention, it helps to begin with an experience reported by some astronauts closer to home. The overview effect describes a shift in perspective associated with seeing Earth as a whole from space. Accounts often emphasize the planet's apparent unity, beauty, fragility, and lack of visible political boundaries. For some observers, the sight has carried strong emotional or philosophical meaning. But the overview effect should not be treated as a universal biological response. Astronauts differ. Their descriptions vary in intensity, language, timing, and interpretation. The term summarizes a reported pattern, not a guaranteed transformation that happens identically to everyone who sees the planet. It also emerged from a particular kind of view. Earth was not a faint point. It was visually available as a world. In low Earth orbit, astronauts see its surface pass beneath them. From the Moon, Earth remains a small but clearly resolved sphere. Radio delay is noticeable in lunar communication, but still short enough for recognizable conversation. Mars offers no equivalent naked-eye image. A telescope can recover more information, and cameras can record the point, but the surrounding sky does not present a blue globe. If the overview effect depends partly on seeing Earth's detail and wholeness directly, a Mars crew may lack the same visual trigger. That absence does not prove an opposite effect. There is no established law saying that a small Earth must produce alienation where a large Earth produces connection. The human mind does not respond to angular size alone. Meaning also comes from expectation, training, personality, culture, crew relationships, mission purpose, prior experience, and the quality of communication with home. The proposed Earth disconnect concern begins where these factors meet physical separation. A crew member knows that Earth contains nearly every other human being, yet receives it through delayed messages and a point of light. The knowledge remains immense, while direct perception becomes minimal. Several mechanisms could contribute without producing one uniform syndrome. Visual reduction may remove a familiar reference. Communication latency may frustrate emotional repair. The inability to return quickly may increase the perceived permanence of conflict or bad news. Operational autonomy may strengthen competence while also increasing responsibility. Confinement and limited privacy may intensify the effect of events originating on Earth. Each mechanism can be studied separately, but the combination may behave differently from its parts. Control is likely to matter. A delayed message chosen voluntarily may feel different from an urgent exchange constrained by physics. A crew member able to schedule private communication may respond differently from someone interrupted during demanding work. A predictable conjunction may be easier to manage than an unexpected equipment failure during ordinary contact. Psychological meaning arises from context, not distance alone. Expectations can also shape interpretation. If crews are told that distress is inevitable, ordinary homesickness may be experienced as evidence of failure. If they are told that training makes them immune, they may hide problems. Accurate preparation should normalize a range of responses while preserving clear paths to clinical help when distress affects health or performance. Possible responses include homesickness, loneliness, altered attachment to Earth, anxiety about events beyond influence, or a stronger identification with the crew and mission. These are plausible possibilities, not measured outcomes from Mars. No human population has yet lived through the complete condition, so severity, frequency, duration, and individual variation remain unknown. Some people may find the point comforting. Its continued visibility could symbolize connection. Predicted communication schedules may provide stability. A crew with strong relationships and meaningful work may adapt well. Others may feel the same point, emphasizes distance rather than reducing it. The physical stimulus can carry different meanings. The mission phase may matter. Early in transit, Earth may still appear larger, and communication delay may be shorter. As distance grows, the crew adapts gradually. Arrival on Mars adds a landscape and daily routine that could create a new sense of place. Conjunction introduces a temporary change in contact. Return reverses some physical conditions while leaving the psychological experience unique to the individual. Even within one crew, responses may change over time. An astronaut might feel awe during the first observation, frustration during a delayed family exchange, confidence during autonomous work, and vulnerability during an unexpected period of uncertainty. Calling the entire mission either inspiring or traumatic would flatten a complex and evolving experience. Researchers therefore look to analogs, but every analog reproduces only part of Mars. Antarctic stations can create isolation, confinement, harsh external conditions, limited evacuation, and long separation from family. Submarines can reproduce enclosed living, small crews, operational discipline, and dependence on life support systems. Simulated habitats can impose restricted space, communication delay, scheduled workloads, and mission-like roles. Space stations provide real microgravity, technical risk, and distance from ordinary society. None places Earth out of view in the Martian sense. Participants in a ground analog know that the surrounding world is physically nearby. A door may be restricted by protocol, but the planet remains outside it. Emergency services may be difficult to reach, yet the light-time barrier does not exist. Communication delay can be imposed by software, but everyone knows it could be removed. That knowledge may influence behavior even when participants take the simulation seriously. A delay created by mission rules and a delay enforced by the speed of light are operationally similar in some tasks, but psychologically different in their irreversibility. On Mars, no authority can decide to restore live contact because morale is falling. The International Space Station provides real spaceflight experience but remains close to Earth. Crews see the planet continuously, and communicate through a large support network. Return can occur far more quickly than from Mars. The station offers valuable evidence about confinement, workload, sleep, teamwork, and technical operations, but not full Earth disconnect. Lunar missions can extend distance and autonomy, especially for operations where direct Earth visibility is limited. They may provide stronger tests of delayed support, local decision-making, and psychological separation. Still, the Moon remains only light seconds away, not light minutes. A lunar crew can experience occulted Earth or communication gaps without reproducing the duration and causal distance of Mars. Analog evidence is therefore useful when claims stay component-specific. A study may reveal how crews handle delayed instructions, monotony, privacy, conflict, workload, or isolation. It cannot establish exactly how humans will react when all those factors combine with years of interplanetary separation and a point like Earth. This is a classic problem of external validity. Conditions measured in one environment do not automatically transfer unchanged to another. The closer an analog matches a particular mechanism, the more confidently it can inform that mechanism. The complete Mars experience remains a combination no existing environment can reproduce. Individual selection may influence adaptation, but selection cannot identify a single personality immune to every stressor. People change under time and context. A trait useful during an emergency may be difficult during routine confinement. Strong independence can support autonomy while complicating cooperation. Emotional openness can support crew cohesion while increasing vulnerability to delayed family news. Crew composition may matter as much as individual resilience. Trust, complementary skills, cultural understanding, conflict style, privacy expectations, and shared mission purpose can shape the social environment. The nearest human world on Mars is the crew itself. A strong team may buffer separation. A damaged team may magnify it. Protective factors may include meaningful work, reliable routines, physical exercise, private space, opportunities for recreation, trusted communication, competent leadership, and confidence in local systems. None is a specific cure for Earth disconnect. They are general conditions that can support human functioning under isolation and stress. Their effectiveness for a Mars crew and the combination required remain open research questions. The Martian environment may provide protective experiences unavailable in sealed terrestrial simulations. Exploration, scientific discovery, movement across a real planetary surface, and the knowledge of accomplishing an unprecedented mission can create purpose. At the same time, danger, workload, dust, restricted mobility, and dependence on the habitat can turn that environment into an additional stressor. Mars is not psychologically empty. It can supply both meaning and pressure. Yet even this should not become a deterministic claim. Compatible people can encounter conflict. Conflict can be repaired. Stress does not equal failure. Psychological risk management seeks to improve probabilities and responses, not predict a fixed destiny. The word disconnect can also mislead if taken too literally. Earth would continue sending messages, data, entertainment, news, scientific support, and personal communication during much of the mission. The crew would retain memories, identities, responsibilities, and relationships formed on Earth. Distance changes access, not necessarily belonging. At the same time, communication does not fully restore presence. A delayed video cannot react to the recipient. News arrives from an earlier Earth. Decisions affecting the mission may be discussed across timelines. The crew can remain socially connected while experiencing a real loss of immediacy. This makes Earth disconnect better understood as a research question than a forecast. Which components matter most? Visual scale, communication delay, mission duration, inability to evacuate, reduced control, separation from family, or the knowledge that all of humanity is concentrated in one distant point. Do these factors add together, interact, or affect different people in different ways? Current evidence cannot rank all of them with confidence for a real Mars crew. That uncertainty is not a weakness to conceal. It is the reason preparation and measurement matter. Mission designers can monitor sleep, mood, performance, conflict, communication patterns, stress physiology, and use of support resources, while respecting privacy and avoiding the assumption that every change signals illness. Researchers can test specific countermeasures in analog environments and during progressively more distant missions. Measurement itself needs a baseline. A change during the mission is interpretable only if researchers understand the person and crew before launch. Repeated measures can reveal trends, yet numbers should be combined with clinical context and self-report. A temporary mood shift after difficult news is not automatically a disorder. Stable task performance does not prove that no distress exists. Small crews also make generalization difficult. The first mission may contain only a handful of individuals selected through exceptional criteria. Their experience cannot establish how every future settler or crew would respond. Later missions may differ in duration, habitat volume, communication infrastructure, purpose, and possibility of return. Earth disconnect may not be one fixed phenomenon across all eras of Mars exploration. Ethics matters here. Crew members should not be treated merely as subjects in an experiment whose risks are unknown. Psychological monitoring can support health, but it can also feel intrusive if every private emotion becomes mission data. Clear consent, confidentiality, clinical support, and limits on operational use are essential. Language matters as well. Describing the first Mars crew as destined to become detached, unstable, or no longer human would be scientifically empty and personally demeaning. The responsible claim is more restrained. Mars introduces a combination of visual, temporal, operational, and social separation that no human has experienced, and specialists consider that combination worthy of serious preparation. The possibility contains both risk and adaptation. Humans have repeatedly formed communities far from familiar surroundings, created rituals of connection, and found meaning in demanding work. Mars is not simply another remote settlement, but past adaptation shows why distance alone cannot predict despair. Nor should courage be confused with immunity. Highly trained astronauts can experience loneliness, grief, conflict, and uncertainty without becoming unfit. A robust mission allows people to acknowledge stress early and use support rather than forcing them to perform in vulnerability. The scientific boundary is now clear. We know the Earth will be point-like. We know communication will be delayed. We know missions may last years and require autonomy. We can identify psychological mechanisms that may matter. We do not know the magnitude of Earth disconnect in the first actual crew. The most responsible forecast is therefore conditional. Separation may create stress, meaning adaptation, or several at once, and evidence must first decide how often, for whom, and under which conditions each appears. Naming the possibility gives the problem a place in mission design. It does not solve it. The next task is to ask what can be rehearsed, supported, or restored before humans encounter the full condition, and what no countermeasure can replace. Preparation begins by refusing to search for one perfect cure. Earth disconnect is not a single machine failure with a replacement part. It is a possible response to several conditions acting together: visual distance, communication delay, limited return options, operational autonomy, confinement, separation from family, and life inside a small crew. A useful countermeasure must therefore identify which part of the problem it addresses. Some conditions can be rehearsed accurately on Earth. Communication delay is one of them. A simulation can prevent messages from arriving until the chosen one-way interval has passed. Mission control can be required to wait before receiving crew reports, and the crew can be required to continue working before guidance returns. The delay can gradually increase to imitate changing planetary distance. Participants then learn which questions need more context, which decisions cannot wait, and which procedures fail when instructors cannot intervene instantly. Such training can expose hidden dependence on real-time help. A habitat team may believe it is autonomous until a simulation removes the ability to ask an immediate follow-up. Engineers may discover that a procedure assumes access to an expert who is not locally available. Medical teams may find that a diagnostic exchange requires too many rounds of clarification. These are valuable findings because designs can change before launch. But imposed delay has a boundary. Everyone knows the restriction is artificial and can be lifted if safety requires it. Participants remain on Earth, surrounded by an accessible world. The exercise can validate protocols and reveal behavior under selected conditions. It cannot prove how the sane people would feel when the delay is physically irreversible. Operational preparation is therefore necessary without being sufficient. Crews can rehearse local decisions, practice using onboard references, and learn to transmit complete evidence packages. Systems can be designed for diagnosis and graceful failure. These measures reduce uncertainty and dependence. They do not restore immediate Earth. Social communication needs its own design. Trying to imitate a live call across a long delay can make the missing immediacy more frustrating. Asynchronous communication accepts the physics. Families and crews can exchange recorded video, voice messages, photographs, writing, and shared projects designed to remain meaningful when received later. Messages can carry context rather than isolated reactions. Timestamps can show which events the sender knew about. Conversation threads can preserve continuity when several replies cross in transit. Crew members can choose communication times that protect sleep and work. Families can receive guidance on how delay changes emotional exchange without being told to suppress difficult news or manufacture constant optimism. This approach preserves relationship, voice, expression, and history. It does not preserve simultaneity. A carefully recorded response still cannot react to the recipient's present emotion. The method works by creating a better form of correspondence, not by disguising correspondence as conversation. Local support remains essential because the nearest immediate response will come from the crew. Private space, trusted peers, clear conflict procedures, recreation, meaningful work, exercise, and access to mental health resources can support functioning. These are broad human performance measures, not proven treatments for Earth disconnect. Remote clinicians may offer delayed support, and some care can be structured around regular exchanges rather than emergencies. Yet conditions requiring immediate intervention still need local capability. Privacy rules must ensure that psychological monitoring does not turn every emotion into a performance report. Crew selection and composition may reduce risk, but no test can certify immunity to an experience that has never occurred. Selection can examine teamwork, adaptability, communication, judgment, and responses to isolation. Long simulations can reveal patterns. They cannot reproduce every future stressor or guarantee that relationships will remain unchanged over years. Training should therefore build skills rather than search for a supposedly perfect personality. Crews can learn conflict repair, cross-cultural communication, emotional self-awareness, leadership transfer, and methods for asking for help early. They can practice responding to another person's distress without assuming it signals weakness or mission failure. The group also needs permission to evolve. Roles that work during transit may change on the surface. A crew member who provides leadership in an emergency may need support afterward. Personal routines may require adjustment as delay, workload, and contact with Earth change. Preparation should create adaptability, not lock people into one predicted response. Visual countermeasures address a different part of the problem. A telescope on Mars could recover more information than the unaided eye. It could help the crew locate Earth, separate it from the Moon under suitable conditions, and sometimes resolve a tiny disk. Cameras could record repeated observations as the geometry changed. For someone who finds the view meaningful, this may strengthen a sense of connection. The telescope cannot make Earth large in the sky, remove solar conjunction, or show the planet in real time. Every photon remains delayed. Weather systems, landscapes, and people remain beyond ordinary resolution. The instrument restores access to an image, not access to Earth's present. Stored imagery can provide far more visual detail. High-resolution photographs, orbital views, landscapes, cities, family spaces, and natural soundscapes could be carried with the mission. Virtual environments might recreate familiar places or present a detailed Earth suspended nearby. Their psychological value for a particular crew would need testing rather than assumption. Virtual Earth solves a problem of representation. It can offer detail, familiarity, and choice when the real planet is point-like or hidden. It cannot become a sensor showing the present state of the world unless current data is transmitted, and any transmitted data arrives late. It can reproduce appearance while leaving causal distance untouched. That limitation does not make it useless. A photograph is not a person, yet photographs matter. A recording is not a live voice, yet recordings preserve connection. Countermeasures do not need to abolish distance to improve life. They need honest goals and evidence showing whether they help without creating new problems. Some crew members may find virtual Earth comforting. Others may find a simulation emphasizes what is absent. Preferences may change with time. Systems should allow personal control and should be evaluated for effects on mood, sleep, attention, and engagement rather than declared beneficial for everyone. Analog research can compare these approaches under controlled conditions. One group might use ordinary delayed messages, while another uses richer asynchronous formats. Visual tools can be tested with or without immersive imagery. Researchers can examine performance, self-reported well-being, communication quality, conflict, and use patterns. Evaluation needs more than asking whether participants enjoyed a tool. A countermeasure might feel comforting while interrupting sleep or reducing attention to crew relationships. Another may initially feel unnatural but improve clarity over time. Useful studies should examine benefits, costs, duration of effect, individual differences, and whether people continue using the system when participation is voluntary. The comparison also needs a realistic workload. A communication format tested during leisure may perform differently during maintenance, illness, or conflict. Virtual imagery used occasionally may have different effects from daily immersion. Countermeasures should be tested within the routines they are intended to support, not as isolated demonstrations. Failure to help is not the only risk. A tool can create dependence. If a crew relies on continuous immersive contact with Earth imagery, a technical failure or conjunction interruption may become more disruptive. Resilience includes the ability to continue when a preferred support is unavailable. The results must remain tied to the tested environment. A benefit during a month-long simulation does not establish effectiveness during a multi-year Mars mission. Small samples, selected participants, awareness of simulation, and the possibility of outside intervention limit generalization. Analog studies refine hypotheses. They do not complete the experiment. Progressively distant missions may improve the evidence. Operations beyond low Earth orbit can test greater autonomy, communication constraints, and periods without direct Earth view. Lunar missions may help examine local decision-making and crew responses to a more remote Earth. Still, light seconds do not reproduce light minutes, and a lunar surface does not reproduce a multi-year Mars timeline. Network infrastructure offers another partial solution. Additional relays may reduce some conjunction disruption or preserve alternate paths. Greater bandwidth can support richer messages, medical data, and immersive media. Delay-tolerant networking can store information until a route becomes available. None removes one-way light time. A high-capacity link can deliver more data after the signal arrives. A relay can redirect a path. Storage can prevent loss. The crew remains unable to receive new information before light has had time to cross the distance. Mission planning can also reduce exposure by choosing trajectories, schedules, and operations that avoid placing critical events inside known communication disruptions. Risky maintenance can be completed earlier. Procedures can be updated before conjunction. Personal messages can be exchanged in advance. These choices reduce avoidable pressure, but the crew still lives through the interval. The most useful preparation may therefore be layered. Engineering creates time and diagnosability. Training builds local judgment. Communication design preserves relationships asynchronously. Visual tools restore selected images. Crew culture provides immediate human support. Earth supplies delayed expertise. Research monitors what helps and changes the plan when evidence demands it. Layers need independent value. If one support fails, the others should not collapse with it. A crew that loses a high-bandwidth link may still have text communication, stored messages, local counseling tools, and peer support. A telescope unavailable during glare does not erase archived imagery. A delayed clinician does not remove the crew's trained medical capability. Redundancy applies to psychological and social support as well as hardware. Personalization must remain bounded by shared operations. Individuals may choose different message schedules, visual environments, recreation, or privacy routines. Yet communication windows, bandwidth, workload, and crew cohesion impose collective constraints. A workable system respects preference without making every support dependent on unlimited resources. The crew should also help design the tools. Systems imposed by distant planners may misunderstand how astronauts actually use limited time and space. Testing with representative users can reveal whether a proposed support feels intrusive, distracting, artificial, or genuinely useful. Continued feedback during the mission allows adjustment, provided changes do not require immediate Earth control. No layer should be asked to solve everything. A telescope cannot repair loneliness. A psychological exercise cannot replace a failed life support component. A relay cannot create a shared present. A strong crew cannot eliminate grief or uncertainty. Resilience comes from overlapping supports with clearly understood limits. There is also a risk in over-engineering connection. Constant monitoring from Earth could undermine the autonomy the crew needs. An endless stream of news might increase distraction or helplessness. Virtual environments could compete with engagement in the actual Martian world. More contact is not automatically better. Timing, content, privacy, and individual choice matter. Preparation should preserve connection without making Earth the only source of meaning. The crew will need routines, relationships, scientific purpose, recreation, and a sense of place on Mars. Adaptation may involve forming a local life rather than spending every moment trying to recreate the one left behind. This is not detachment by definition. Human beings can belong to more than one place and maintain distant relationships while building a present environment. Whether Mars crews experience that process as expansion, loss, or both remains an open question. The final evidence gap cannot be closed from Earth. Simulations can combine delay, confinement, workload, and limited contact. They cannot make participants millions of kilometers away. Lunar missions can increase distance. They cannot reproduce the full journey, duration, or communication geometry. Only humans traveling to Mars will create the complete condition. That fact imposes a moral responsibility. The first crew should not be sent as an uncontrolled psychological experiment. Preparation must use the best available evidence, monitor risk, protect privacy, provide support, and preserve options. At the same time, uncertainty must be disclosed honestly, because no program can guarantee the human outcome. Consent does not end at launch. Monitoring plans, access to sensitive records, and the boundary between medical care and research should be defined clearly. Crew members need ways to report distress without automatically threatening their status. Researchers need data, but the mission needs trust. A system that drives people to hide their experience defeats both goals. The available tools can reduce preventable burdens. They can make operations safer, messages richer, support more accessible, and visual connection more detailed. They can help people understand what they are experiencing. Preparation can improve probabilities, preserve choices, and reduce avoidable harm. It cannot convert an unprecedented mission into a condition already proven safe for every mind involved. They cannot make Earth immediate. Once every proposed solution reaches that boundary, the title can finally be answered without exaggeration. We can separate what disappears temporarily, what physics removes for the mission, and what may change in the people who go.